Today we step into one of the deepest questions in modern physics, a question that touches the edges of gravity, information, thermodynamics, and the very shape of space-time itself. We begin with the familiar world of Newton and Einstein, where gravity bends paths, curves the fabric of space-time, and guides the motion of planets and galaxies. Yet beneath that familiar surface lie puzzles that have resisted explanation for decades. These puzzles are not speculative curiosities, but the very cracks where our greatest theories collide. Singularities that swallow information, quantum laws that refuse to blend peacefully with curved geometry, horizons that behave like hot surfaces, even though nothing should be there at all. As the story unfolds, we will explore why black holes possess entropy and temperature, why an accelerating observer sees a warm glow in what should be empty space, and how these clues hint that space-time itself may carry hidden microscopic structures. We journey through the holographic principle and the remarkable correspondence known as ADS-CFT, where gravity in a higher dimensional space emerges naturally from a theory without gravity in fewer dimensions. This duality does not describe our universe directly, but it reveals something astonishing. In certain precise settings, gravity is not fundamental. It is the large-scale reflection of deeper information. Then we examine Eric Verlinde's proposal that gravity might be an entropic force. We look at how he derived Newton's law from simple information-based arguments, how he attempted to describe galactic motion without dark matter, and what subsequent observations revealed about the strengths and limits of this idea. Some predictions match broad galactic behavior. Many do not. The evidence remains firmly on the side of general relativity and dark matter, yet the idea continues to push physicists toward new ways of thinking about space-time. We also explore the frontier where quantum entanglement helps shape geometry, where networks of information weave together to form the distances and surfaces of a space that grows from microscopic correlations. These insights are mathematically solid in certain models and have become central to research on the deep structure of space-time. By the end, we confront the conclusion that modern evidence does not show gravity to be an entropic force, but the thermodynamic and information-based ideas behind this proposal may still be pointing towards something profound. They reveal that gravity, entropy, and quantum information are not separate stories. They are threads of a larger tapestry we are only beginning to see. This is what we explore today: the known, the unknown, the experimentally confirmed, and the mathematically suggested. A journey through the frontier where gravity meets information and where space-time itself may hold hidden layers waiting to be understood. Gravity enters our lives so quietly that we rarely pause to consider how strange it truly is. It acts with unwavering persistence, shaping every movement we make, yet it remains almost invisible to our senses. We feel its pull without ever seeing its source. We trust it without understanding its origin. From the fall of a stone to the orbit of a planet, gravity conducts the universe with a steady hand, ancient and familiar. But familiarity can be deceptive. The closer we look, the more gravity begins to resemble a puzzle disguised as a law of nature. The earliest attempts to describe this mysterious pull were rooted in observation and intuition. People watched objects fall for countless generations before anyone could express the idea in a mathematical form. When Newton finally did so, it seemed as though a new window had opened into the workings of the universe. His law of universal gravitation unified two worlds that once felt distinct. The apple falling from a branch and the moon orbiting the Earth followed the same rule. For the first time, the heavens and the Earth obeyed a single mathematical principle. This unity was astonishing, a revelation that changed the course of science forever. Yet even at the height of his achievement, Newton sensed an unsettling truth. He could describe how gravity worked, but he could not explain what caused it. He wrote down the law, but he did not know the mechanism. The force acted across empty space, silent and instantaneous, as if distance meant nothing. This troubled him deeply. He understood the precision of the results, but not the underlying reason for their existence. Gravity remained a mystery, wrapped in an equation that worked flawlessly, but revealed little about its true nature. Centuries later, Einstein arrived and reshaped the entire picture. He imagined space and time not as separate entities, but as a unified fabric capable of bending, stretching, and warping. Mass and energy did not simply attract each other. They sculpted the geometry around them, and objects moved along the curves of that geometry. A planet orbiting a star was no longer pulled by an invisible force. It followed the natural path within a curved space-time. This idea was revolutionary, and its predictions were soon confirmed with extraordinary accuracy. Light bent around massive objects. Time slowed in strong gravitational fields. The very shape of the universe changed under the influence of matter. Einstein's theory was so elegant and so successful that it became the foundation on which modern cosmology rests. Yet even this profound vision reveals its limits under certain conditions. At the center of a black hole, space-time curves so sharply that the mathematical description collapses into a singularity. At the earliest moments of the universe, the equations predict densities and temperatures that defy physical meaning. These singularities are signs that the theory cannot explain everything. They mark places where the classical description reaches a boundary beyond which new principles must operate. The most surprising clues come from black hole thermodynamics. When Jacob Bekenstein suggested that black holes possess entropy, it challenged every intuition about the simplicity of these objects. Hawking later demonstrated that they emit radiation due to quantum effects near the horizon. This radiation has a temperature, and the entropy is proportional to the area of the horizon measured in Planck units. This discovery was more than a theoretical insight. It revealed a deep link between gravity, quantum mechanics, and thermodynamics. Black holes behave not as purely geometric entities, but as thermodynamic systems with hidden microscopic degrees of freedom. Entropy usually counts the number of microscopic states available to a system. If a black hole possesses entropy, then it must possess hidden states. But the fact that the entropy scales with area rather than volume suggests something far more startling. The information describing a gravitational system appears to be encoded on its boundary. This area scaling contradicts the behavior of ordinary matter and forces us to question how spacetime stores information. It hints that spacetime might not be fundamental, but emergent from something deeper. Another clue arises from the Unruh effect, which reveals that an accelerating observer perceives a warm bath of particles, even in what others see as empty space. This temperature depends on acceleration, not on any physical heat source. It connects motion, quantum fields, and thermal behavior in a way that classical physics cannot explain. Together with black hole thermodynamics, it suggests that spacetime carries an intrinsic thermodynamic structure. If spacetime exhibits thermodynamic behavior, then gravity itself may be the macroscopic result of microscopic information. Temperature arises from the motion of atoms. Pressure arises from collisions too small to observe individually. Perhaps gravity arises from deeper degrees of freedom, whose collective behavior shapes the world we see. This possibility does not weaken Einstein's legacy. Instead, it extends his insight, suggesting that the curvature he described may be one layer of a more intricate reality. These clues do not yet reveal the full structure of that reality, but they provide the motivation for questioning the fundamental nature of gravity. If black holes carry entropy, if acceleration produces temperature, and if spacetime behaves like a thermodynamic system, then the traditional view of gravity may not tell the whole story. To explore the deeper truth, we must first understand the classical picture thoroughly. Only then can we examine whether gravity might be an emergent phenomenon arising from hidden degrees of freedom. Gravity has always appeared as a calm and continuous presence, shaping the world so quietly that we rarely notice its subtleties. Yet when we examine it with scientific precision, its familiar pull, begins to reveal a network of tensions that stretch across the deepest layers of physics. These tensions do not undermine the usefulness of classical theory. Instead, they illuminate the places where that theory can no longer describe reality without contradiction. Every scientific advance comes from finding the boundary between what we understand and what we only think we understand, and gravity brings us to that boundary with unusual clarity. The classical picture treats space-time as smooth and unbroken, a continuous fabric that bends gently around massive bodies. In this view, the smallest scales are simply smaller regions of the same geometry. But quantum mechanics suggests that such smoothness cannot persist indefinitely. At extremely small distances, fluctuations in energy and geometry become too intense for the classical picture to remain valid. The uncertainty principle prevents any region of spacetime from being perfectly still, and these fluctuations grow stronger as the scale shrinks. If spacetime must respond to these fluctuations, then its smoothness may be an illusion that holds only when viewed from far above its true microscopic structure. This tension becomes sharper when we examine the precise behavior of horizons. Event horizons, acceleration horizons, and even cosmological horizons seem to carry temperature and entropy, properties normally associated with systems made of many constituents. If these horizons possess thermodynamic character, they must reflect underlying microstates. But these microstates do not appear in the classical equations of general relativity. The geometry of spacetime alone cannot store entropy. It has no mechanism for counting states. This means that something beneath the geometry must provide the microscopic structure from which entropy arises. The thermodynamic behavior of horizons is thus not an optional clue. It is a direct signal pointing to deeper physics. Black holes provide the most dramatic example of this principle. The Bekenstein-Hawking formula tells us that the entropy of a black hole is proportional to the area of its horizon measured in Planck units. This area is staggeringly small compared to everyday scales, yet the entropy of even a modest black hole is enormous. If every bit of that entropy corresponds to a microscopic state, then the number of such states is unimaginably large. This raises a troubling question. Where are those states located? They cannot reside inside the black hole in the usual sense, because the entropy does not scale with volume. Instead, it scales with the surface area. This suggests that the true microscopic description of a gravitational system may live on a lower dimensional boundary that encodes the information needed to describe the interior. This insight gave rise to the holographic principle, an idea that has reshaped how physicists think about spacetime. The principle proposes that the information content of a region of space is determined not by the volume of that region, but by the area of its boundary. If true, it means that the three-dimensional world we see may be a large-scale manifestation of information encoded on a two-dimensional surface. This does not mean that the world is literally a projection. Instead, it means that the mathematical structure underlying gravity may be organized in this surprising way. The fact that black hole entropy naturally follows an area law strongly suggests that the holographic principle is not a mathematical curiosity, but a reflection of a deep property of nature. Quantum mechanics introduces further tension by demonstrating that information cannot simply disappear. But classical black holes seem to swallow information without limit, hiding everything behind the horizon. If gravity were purely classical, information falling into a black hole could vanish forever. But quantum theory forbids such loss. This conflict, known as the information paradox, is not merely an academic puzzle. It forces us to reconsider the very foundation of space-time. If information must be preserved, then the geometry of a black hole must contain some mechanism for storing or transforming that information. Classical geometry alone cannot perform this task. Something deeper must support the conservation of information, further hinting that the geometry itself is emergent. The conflict between general relativity and quantum mechanics becomes particularly intense when we examine regions of extreme curvature, Near singularities, the equations of relativity predict that curvature becomes infinite, but quantum theory insists that physical quantities cannot diverge in this way. The existence of singularities therefore signals not a real physical condition, but a breakdown of the classical picture. The theory does not fail because nature behaves badly. It fails because the mathematical structure we use to describe nature is incomplete. There must be a deeper framework in which curvature does not blow up and information does not vanish. Many physicists suspect that this deeper framework will not resemble the continuous geometry of relativity, but will instead involve more fundamental degrees of freedom from which geometry emerges. Even in less extreme settings, the evidence points toward an underlying structure. Accelerating observers perceive a thermal bath of particles, where inertial observers perceive vacuum. This effect arises from the behavior of quantum fields and reveals that temperature depends on the observer's motion through spacetime. The existence of this temperature suggests that spacetime itself behaves like a medium with thermodynamic properties. If temperature can appear in empty space, then empty space may not truly be empty. Instead, it may possess a structure that becomes visible only under certain conditions. That structure may be responsible for the emergence of gravity at large scales. The accumulation of all these clues suggests that our understanding of gravity may be incomplete, not because the classical theories are wrong, but because they are describing a macroscopic phenomenon that arises from microscopic principles. Just as the smoothness of water hides the motion of countless molecules, the smoothness of spacetime may hide the behavior of deeper degrees of freedom. If this is true, then gravity is not a fundamental influence, but a property that emerges from the collective behavior of those degrees of freedom. This idea does not diminish the value of classical gravity. Instead, it places that theory within a larger context, one that may ultimately reveal what spacetime is made of. The more we examine these clues, the more gravity begins to look like a phenomenon that conceals its true origin behind the quiet elegance of its behavior. The classical description works so smoothly that it can disguise the possibility that something deeper is controlling the form and structure of spacetime itself. Yet every major tension between general relativity and quantum mechanics pushes us toward the idea that gravity may not stand alone as a fundamental force. Instead, it may be the large-scale signature of microscopic processes that govern the flow of information throughout the universe. These processes would operate beneath the familiar fabric of spacetime, hidden from direct observation but shaping everything we see. To make sense of this possibility, consider how emergent phenomena behave in familiar systems. A glass of water appears smooth and continuous, yet it is composed of molecules constantly colliding and moving. Temperature, a concept central to the description of water, does not exist at the level of individual molecules. It emerges only when many molecules interact and create collective behavior. Pressure behaves the same way. It is not a force applied by a single molecule, but a macroscopic effect arising from countless microscopic impacts. In both cases, the emergent quantities are essential for describing the system at large scales, even though they do not appear in the fundamental laws governing the constituents. Gravity may behave similarly. If spacetime has microscopic degrees of freedom, then curvature could be the large-scale result of how those degrees of freedom arrange themselves. The geometry described by general relativity would then be an emergent property, not a fundamental one. This idea gains strength from the thermodynamic behavior of horizons. When a horizon possesses temperature and entropy, it behaves like a thermodynamic system with many internal degrees of freedom. Yet the classical description of spacetime does not include any such degrees of freedom. This mismatch suggests that geometry itself may arise from an underlying structure in the same way that fluid behavior arises from molecular interactions. Another important clue lies in the way gravity interacts with information. In classical physics, information about the initial state of a system determines how that system evolves. But in gravitational systems, the presence of horizons complicates this picture. Information entering a black hole crosses the horizon and becomes inaccessible, Yet quantum mechanics insists that information cannot be destroyed. Reconciling these two principles requires a deeper understanding of how information is stored and processed in gravitational systems. The fact that black hole entropy scales with area rather than volume hints that the storage mechanism is not located inside the black hole in any ordinary sense. Instead, it suggests that information is encoded on the horizon itself, pointing again toward a lower dimensional framework beneath the familiar three-dimensional world. Such insights bring us to an important realization. The clues suggesting that gravity is emergent do not come from speculative theories or untested ideas. They arise from well-established principles of quantum mechanics, thermodynamics, and general relativity. Each principle works exceptionally well within its own domain, but the combination of all three reveals tensions that classical theory cannot resolve. These tensions do not weaken the credibility of general relativity. They highlight its role as a macroscopic description that may emerge from something more fundamental. The challenge is to understand what that more fundamental structure might be and how it gives rise to the geometry we observe. The holographic principle provides one possible path toward that understanding. It suggests that the true degrees of freedom governing a region of spacetime are encoded on its boundary, not within its volume. If this is correct, then spacetime itself may be constructed from informational relationships that live on these boundaries. Gravity would then arise from the way this information organizes itself, much like the shape of a soap film arises from the way molecules arrange themselves to minimize energy. The geometric picture of spacetime would still be valid, but it would be a derived picture rather than a fundamental one. This possibility challenges our intuitions about space, but it aligns with everything we have learned from black hole entropy and quantum field theory. Yet even with these insights, it is important to remain grounded in established science. Nothing currently proves that gravity is emergent. General relativity continues to succeed across an astonishing range of experiments. The bending of light, the behavior of atomic clocks, the motion of binary stars, and the patterns of gravitational waves all match its predictions with remarkable precision. Any emergent theory must reproduce these successes perfectly. It must explain why the classical picture works so well and show how that picture arises from deeper principles. This requirement does not weaken the emergent perspective. It strengthens it by demanding that any new ideas remain consistent with observation. The purpose of this chapter has been to uncover why physicists even consider the possibility that gravity might not be fundamental. It is not a matter of replacing one idea with a new one out of creative curiosity. It is a matter of following the clues revealed by nature itself. Black hole, thermodynamics, quantum vacuum behavior, information preservation, and holographic principles all point toward a structure beneath spacetime. These clues suggest that gravity might be the macroscopic expression of that structure, emerging from hidden degrees of freedom in the same way that temperature emerges from molecular motion. Whether or not this perspective proves correct, it provides a powerful motivation for exploring the deepest layers of the universe. To understand what gravity truly is, we must first understand the classical world with complete clarity. Only then can we investigate the possibility that the geometry of spacetime arises from something more fundamental. This exploration begins by examining the classical foundations laid by Newton and transformed by Einstein, foundations that remain essential even if gravity ultimately emerges from a deeper reality. Gravity entered scientific thought long before anyone understood its true nature. Yet its effects were recorded with quiet precision by every civilization that watched the heavens. The slow drift of stars across the night sky, the steady dance of planets, the rhythmic rise of tides, and the reliable fall of objects all testified to an unseen influence guiding the world with gentle authority. For centuries, these patterns remained unexplained, familiar but mysterious, until a profound shift occurred when mathematics offered a language capable of capturing their harmony. This shift marked the beginning of a new era in which gravity transformed from an intuitive idea into a scientific law whose clarity shaped the course of physics. When Newton introduced his law of universal gravitation, the world expanded in a single stroke. He proposed that every mass in the universe attracts every other mass with a force that depends on their separation and their sizes. This idea was astonishing in its simplicity and breathtaking in its scope. For the first time, a single equation could describe falling apples and the orbital motion of planets. The Earth no longer stood apart from the heavens. Both obeyed the same rule. This unity was unprecedented in science, revealing that the cosmos followed mathematical laws rather than the whims of celestial spheres or divine patterns. The elegance of Newton's law lay in its precision. It predicted not only the general motion of planets, but the fine details of their orbits. Comets followed paths that could now be calculated. Tides could be explained by the combined gravitational pull of the Moon and the Sun. For centuries, this framework served as the backbone of astronomy and mechanics. Yet Newton's achievement, extraordinary as it was, carried an unease that he himself acknowledged. The idea that masses could attract each other across empty space without any medium disturbed him deeply. He could measure the attraction, calculate its strength, and predict its behavior, but he could not explain its cause. Gravity acted instantaneously across distance, faster than any signal or influence known at the time. This instantaneous action challenged intuition and sparked philosophical debate. Newton accepted the law empirically, but never claimed to understand its underlying mechanism. It became clear that although the law worked perfectly, it left unanswered questions about the nature of space, time, and the transmission of force. As scientific tools grew more refined, small discrepancies began to emerge when observations reached new levels of precision. The orbit of Mercury, for example, deviated slightly from the path predicted by Newton's law. This deviation was tiny, almost imperceptible, yet it was persistent and measurable. Astronomers searched for explanations, proposing hidden planets or unnoticed matter, but none of these ideas solved the puzzle. It was a hint that the classical framework, for all its power, was incomplete. Something deeper governed the motion of planets, something that Newton's formulation could not fully capture. Einstein offered that deeper explanation by reshaping the very structure of space and time. His insight began with the equivalence of inertial and gravitational mass. Objects in free fall experience weightlessness not because gravity disappears, but because they follow natural paths through space-time. This equivalence led him to a new vision in which gravity was not a force at all. It was the curvature of space-time caused by mass and energy. In this picture, space-time behaves like a flexible fabric. When a massive object, such as a star or planet, is present, the fabric curves around it, creating pathways that other objects follow. A planet does not orbit a star because it is forced to do so. It orbits because space-time curves in such a way that a circular or elliptical path becomes the natural route. This geometric interpretation revolutionized physics. Suddenly, the deflection of starlight near massive bodies was not a mysterious phenomenon, but a straightforward consequence of curved space-time. Objects moving at high speeds or under strong gravitational influence experience time differently, leading to measurable effects in clock rates and particle behavior. These predictions were not philosophical musings, but concrete results that could be tested. The bending of light during a solar eclipse provided one of the earliest confirmations. Later, atomic clocks on Earth revealed measurable differences depending on their altitude. Even technologies like global positioning systems rely on these gravitational time shifts to remain accurate. Einstein's theory did not merely replace Newton's. It expanded it, exposing layers of structure that were invisible in the classical description. Despite its elegance, the geometric framework of general relativity also revealed its limitations as research pushed into extreme conditions. Black holes, formed when massive stars collapse under their own gravity, contain regions where curvature becomes so intense that space-time seems to fold into a point. These singularities mark the breakdown of the theory, places where the equations can no longer describe physical reality. Similarly, when the universe is traced backward to its earliest moments, the theory predicts a state of infinite density. These infinities are not physical predictions. They are indications that general relativity cannot describe the world at the deepest scales. They reveal that the classical description, though remarkably accurate on large scales, is incomplete. The clash between general relativity and quantum mechanics sharpens this realization. Quantum mechanics governs the behavior of particles and fields with extraordinary precision. It describes uncertainty, wave-particle duality, and the fluctuations inherent in the vacuum. But when we attempt to quantize gravity using the same techniques, the mathematical expressions explode into divergences that cannot be renormalized. The smooth space-time of relativity and the restless quantum world cannot coexist within the same framework without contradiction. This incompatibility lies at the heart of modern theoretical physics and motivates the search for a deeper theory. The strength of the classical framework becomes clear even as its limitations appear. Newton's law and general relativity describe almost every gravitational phenomenon we have observed. The motion of planets, the bending of light, the behavior of binary stars, and the waves produced when black holes collide all follow predictions that match observation with astonishing precision. Any theory that claims to lie beneath gravity must explain why these classical descriptions work so well. It must reproduce their predictions exactly in the appropriate limits. It must account for every successful test of gravitational physics, from laboratory experiments to observations across billions of light years. The purpose of examining this classical picture is not to discard it, but to understand the standard any emergent explanation must meet. Gravity, whether fundamental or emergent, must align with the measurable behavior of the universe. The foundations laid by Newton and transformed by Einstein remain essential because they describe the world as we experience it. If gravity arises from deeper microscopic principles, those principles must give rise to the curvature and force-like behavior that classical physics describes so well. Einstein's geometric vision of gravity brought a new sense of unity to the physical world. Yet it introduced a profound conceptual shift that transformed more than just the mathematics. It redefined the very nature of space and time. Instead of existing as a passive stage where events occurred, space-time became an active participant in the unfolding of physical processes. It could stretch, bend, twist, and ripple, responding dynamically to the presence of mass and energy. This idea was more than elegant. It was necessary to reconcile the principle of relativity with the constant speed of light. The structure of space-time had to adjust itself so that all observers, regardless of their motion, would agree on the laws of physics. One of the most striking consequences of this new framework was the realization that the geometry of space-time determined how clocks tick. A clock placed closer to a massive object runs more slowly than one placed farther away. This is not a mechanical effect of gravity tugging on the clock. It is a manifestation of space-time curvature. Time itself stretches differently depending on the gravitational environment. This behavior has been confirmed through experiments involving atomic clocks separated by mere meters in height. These clocks reveal subtle differences in the passage of time, proving that Einstein's equations describe reality with extraordinary precision. The fact that such a small change in altitude can alter the flow of time hints at how deeply geometry influences the behavior of the universe. Another remarkable prediction of general relativity is the existence of gravitational waves, ripples in spacetime generated by massive objects in motion. For decades, these waves remained theoretical, too faint to detect with available technology. But in the early 21st century, scientists observed the first direct signal from colliding black holes. The pattern of the wave carried detailed information about the masses and motions of the objects involved. The signal matched the predictions of general relativity with stunning accuracy. This observation was a triumph for Einstein's theory, demonstrating not only its elegance, but its physical truth. Gravitational waves showed that spacetime is not a static backdrop, but a dynamic entity capable of carrying information across the cosmos. Yet even with these remarkable confirmations, cracks appear when the classical theory attempts to describe extreme environments. Near a singularity, the curvature becomes so intense that the equations cease to function. The concept of spacetime loses meaning. Distances, times, and paths all collapse into a single undefined point. This breakdown is not merely a mathematical inconvenience. It signals that the theory cannot describe what happens when gravity becomes overwhelmingly strong. Something beyond the classical framework must replace the singularity with a more fundamental description. The smooth geometry of relativity must give way to a deeper structure that remains well-behaved even in the most extreme conditions. This need for deeper structure becomes even clearer when we consider the interplay between gravity and quantum mechanics. In quantum field theory, forces arise from the exchange of particles. Electromagnetism is mediated by photons, the strong interaction by gluons, and the weak interaction by heavy-gauge bosons. If gravity were a fundamental force of the same kind, we would expect a particle called the graviton to mediate gravitational interactions. However, attempts to construct a quantum theory of gravity using this approach encounter severe difficulties. The resulting expressions diverge uncontrollably, and the theory resists renormalization. This resistance is not a flaw in technique. It reflects a deeper incompatibility between the smooth continuum of spacetime and the discrete, probabilistic nature of quantum mechanics. Quantum fluctuations complicate this picture further. According to quantum theory, the vacuum is not empty, but filled with virtual particles constantly appearing and vanishing. These fluctuations become stronger at smaller scales. If spacetime is truly continuous, then these fluctuations would distort it infinitely at the smallest conceivable distances. Such behavior is inconsistent with any stable physical world. The existence of a minimum meaningful scale for spacetime, often associated with the Planck length, suggests that spacetime may possess a granular or discrete structure hidden beneath the classical continuum. If true, then the geometry of relativity would be an approximation, valid at large scales, but replaced by something more fundamental at extremely small scales. The classical framework offers yet more tension when we consider energy conditions. These conditions, which constrain the types of matter that can curve spacetime in certain ways, work well for familiar forms of matter, but fail in quantum contexts. Quantum fields can violate energy conditions locally and temporarily, a behavior allowed by the uncertainty principle. These violations permit exotic phenomena, such as negative energy density. While such effects are typically small and fleeting, they highlight the fact that classical spacetime does not fully incorporate the rules of quantum physics. Any theory that unites gravity and quantum mechanics must account for these quantum violations without permitting unphysical behavior on large scales. Despite all these tensions, the classical description of gravity remains astonishingly successful. It predicts the motion of planets, the bending of light, the time delay of signals near massive bodies, and the patterns of gravitational waves. It describes the large-scale structure of the universe, including the expansion of galaxies and the evolution of cosmic background radiation. These successes demonstrate that any deeper theory must reduce to general relativity under appropriate conditions. The classical framework is not a stepping stone to be discarded. It is a fundamental requirement that anchors any attempt to understand whether gravity might emerge from microscopic principles. If gravity is emergent, the classical picture must be the large-scale limit of that emergence. It must arise naturally from the collective behavior of the underlying degrees of freedom. This requirement places strict constraints on any theory of emergent gravity. It must not only explain why space-time appears smooth at large scales, but also reproduce the exact geometric behavior described by general relativity. The curvature, the geodesics, the gravitational waves, and the time dilation must all emerge from deeper principles in a way that matches observation. The classical framework therefore serves as both guide and challenge. It illuminates the structure of gravity as we observe it and sets the standards any alternative must meet. Newton revealed gravity as a universal attraction. Einstein revealed it as the curvature of spacetime. The next step in our exploration is to examine whether these descriptions, extraordinary as they are, might themselves arise from a deeper realm of physics. The extraordinary precision of the classical framework becomes even more striking when we examine how deeply it is embedded in the behavior of the universe. Every satellite that orbits Earth follows a path shaped by Newtonian principles, corrected by relativistic adjustments. Every atomic clock aboard those satellites ticks at a different rate than clocks on the ground, a difference predicted with exactness by general relativity and confirmed in practice every moment. Without accounting for these relativistic effects, navigation systems would drift by kilometers each day. This dependence on geometric time dilation demonstrates that the classical description is not merely theoretical. It is woven into the technologies we use to measure and explore the world. On larger scales, Newton's and Einstein's ideas shape the evolution of stars, galaxies, and clusters of galaxies. The life cycle of a star, from the collapse of a gas cloud to the ignition of nuclear fusion, and finally to the star's transformation into a white dwarf, neutron star, or black hole, is governed by the balance between pressure and gravity. This process unfolds over millions or billions of years, guided by the classical laws that dictate how mass and energy curve spacetime. The formation of galaxies follows similar principles. Small density fluctuations in the early universe grew under gravitational influence, forming structures that merged to create the galaxies we observe today. These vast cosmic patterns obey the equations of general relativity, even as they operate on scales far beyond human experience. The classical framework also provides a coherent explanation for the expansion of the universe. When Einstein first applied his equations to cosmology, he discovered that the universe could not remain static. It must either expand or contract. Later observations confirmed the expansion and revealed that distant galaxies recede from us with speeds proportional to their distance. This behavior follows naturally from the geometry of space-time. The stretching of space-time itself carries galaxies apart, and the rate of that stretching is described by the equations of general relativity. The discovery of cosmic acceleration later added complexity, suggesting that an unknown form of energy contributes to the expansion. Even so, the overall framework remains grounded in classical gravitational theory. These successes create a striking paradox. General relativity works extraordinarily well, yet it cannot be the final description of gravity. It contains singularities where it breaks down. It cannot merge with quantum mechanics. It predicts behaviors that contradict fundamental principles, such as the conservation of information. These contradictions do not diminish the power of the classical framework. They reveal that it is an approximation, an effective description that must emerge from deeper physical laws. Just as the equations of fluid dynamics emerge from the collective behavior of molecules, the equations of general relativity may emerge from interactions far below the scale where spacetime appears smooth. This idea gains further support from the way energy and momentum appear in the classical framework. In general relativity, energy tells spacetime how to curve, and curvature tells matter how to move. This relationship is encoded in the Einstein field equations, which relate the curvature of spacetime to the distribution of mass and energy. These equations are elegant and powerful, yet they contain a subtle detail. They do not specify the microscopic origin of mass or energy. They describe how mass and energy influence geometry, but not what mass and energy fundamentally are. This distinction leaves room for a deeper explanation. If mass and energy themselves arise from microscopic structures, then the curvature they produce may also be emergent. Even the concept of inertial motion hints at deeper principles. Objects move along geodesics, the natural paths determined by spacetime geometry. These paths require no force, only the curvature of the environment. But if spacetime geometry emerges from a deeper informational or quantum structure, then geodesics might reflect the statistical behavior of that underlying system. The apparent force of gravity then becomes a manifestation of how information is distributed and processed at the microscopic level. This perspective does not contradict the classical picture. It explains why the classical picture works. To appreciate how this emergent behavior might operate, imagine a surface composed of countless tiny elements. When viewed from far away, the surface appears perfectly smooth. But as we zoom in, the individual elements become visible. Their arrangement determines the shape of the surface at large scales. Similarly, if space-time is composed of discrete informational units, then its smooth geometric behavior would emerge only when viewed on scales large enough to obscure those units. The curvature that guides planets and light would be the collective behavior of underlying structures too small to observe directly. Another clue comes from the behavior of gravitational waves. These waves propagate through space-time as gentle ripples, carrying energy across billions of light years. Their existence confirms that space-time can behave like a medium, yet no particle or substance within classical theory accounts for this capability. If space-time is emergent, then gravitational waves might be vibrations in the underlying structure, similar to sound waves in a material. Their smooth propagation over vast distances demonstrates the coherence of this structure at macroscopic scales, even if the microscopic details remain hidden. The remarkable success of general relativity therefore becomes a guide to the hidden architecture of the universe. Any deeper theory must reproduce the classical predictions exactly for macroscopic behavior. The bending of starlight, the passage of time in gravitational fields, the precession of orbits, and the propagation of gravitational waves must all arise naturally from the deeper structure. The classical framework does not prevent us from exploring emergent ideas. It provides the constraints that any emergent explanation must satisfy. This chapter brings us to a crucial understanding. The classical description of gravity is powerful, elegant, and essential, but it is not complete. Its limitations hint at a deeper reality in which space-time and curvature may arise from microscopic principles that remain hidden from view. By examining the classical framework in detail, we establish the foundation on which any emergent model must stand. The search for the deeper nature of gravity begins not by discarding Newton and Einstein, but by recognizing that their achievements form the surface of a much larger and more mysterious structure. The classical picture of gravity paints a world shaped by geometry, where mass and energy bend the fabric of space-time and objects follow the curves created by that bending. For a long time, this view seemed complete, a graceful unification of physics that needed no further explanation. Yet as researchers pushed deeper into the mathematics of black holes and the behavior of quantum fields, they discovered something unexpected. Gravity, the force that shapes the cosmos, appeared to share a hidden connection with thermodynamics, the branch of physics that describes heat, temperature, and entropy. This connection emerged not from speculation, but from precise calculations, revealing that space-time, which once seemed purely geometric, might possess a thermodynamic character beneath its smooth surface. The first hint of this connection arrived when Jacob Bekenstein proposed that black holes should possess entropy. Classical physics offered no place for such a concept. A black hole appeared to be a simple object defined entirely by mass, charge, and angular momentum. It contained no internal complexity to account for thermodynamic behavior. Entropy, however, measures the number of microscopic states a system can occupy. If a black hole possessed entropy, then it must contain microscopic degrees of freedom. This idea was troubling because classical general relativity provided no such degrees of freedom. The event horizon was a geometric boundary, not a physical membrane. Yet Bekenstein argued convincingly that the horizon's area measured in Planck units behaved like entropy. This suggestion challenged the classical understanding of both black holes and space-time. The challenge became even stronger when Stephen Hawking discovered that black holes emit radiation due to quantum effects near the horizon. This radiation has a temperature inversely proportional to the mass of the black hole. The existence of this temperature means black holes obey the laws of thermodynamics. They radiate energy, possess entropy, and follow a version of the first law of thermodynamics connecting energy, temperature, and entropy. Hawking's result was not an approximation or a conjecture. It was a precise calculation based on quantum field theory in curved spacetime. This was the moment when gravity and thermodynamics became undeniably linked. A black hole was no longer a cold, silent object. It was a thermodynamic system with temperature and entropy that emerged from the interplay between quantum mechanics and classical geometry. The idea that a geometric feature of spacetime could behave like a thermodynamic system forced physicists to reconsider the nature of spacetime itself. If horizons possess entropy and temperature, they must conceal underlying microstates. But general relativity treats spacetime as smooth and continuous, with no internal structure. Something was missing. Either the classical picture was incomplete, or the concepts of temperature and entropy had to be interpreted in a new light. Many researchers came to believe the first possibility was correct. The smooth geometry of spacetime might be an emergent phenomenon, similar to how the smoothness of water emerges from the motion of countless molecules. Additional support for this thermodynamic perspective came from the study of accelerated observers. According to the Unruh effect, an observer undergoing constant acceleration perceives empty space as filled with a warm bath of particles. The temperature of this bath increases with acceleration. This means that temperature can arise not from matter, but from the structure of spacetime itself. The vacuum is not an empty void. It is a dynamic environment shaped by quantum fluctuations. When an observer accelerates, they interact with these fluctuations in a way that produces thermal radiation. This behavior is not a theoretical guess. It follows directly from quantum field theory and demonstrates that temperature is inherently tied to motion and horizon structure. The combination of these insights suggests that thermodynamic behavior is woven into the fabric of spacetime. Black hole horizons behave like heat-absorbing surfaces, and acceleration produces temperature even without matter. These phenomena point toward a deeper unity between gravity and thermodynamics. If spacetime carries microscopic degrees of freedom, then gravity might be the statistical behavior of those degrees of freedom. Curvature could be the macroscopic expression of how the underlying structure organizes itself. This idea mirrors the way temperature arises from the motion of atoms. No single atom possesses temperature, yet temperature becomes meaningful when many atoms interact. Similarly, if gravity emerges from microscopic processes, its familiar behavior would arise only when spacetime is viewed on large scales. These thermodynamic phenomena also reveal something surprising about the nature of information in gravitational systems. The entropy of a black hole is proportional to the area of the horizon, not the volume of the interior. This violates the intuition built from ordinary matter, where entropy scales with volume. The area scaling suggests that the true degrees of freedom reside on the horizon, not inside it. This is the foundation of the holographic principle, which asserts that the information content of a region of space can be encoded on its boundary. While this principle arose from the study of black holes, it may apply far beyond them, hinting that the universe itself could be described in terms of boundary information. The idea that spacetime behaves thermodynamically does not replace general relativity. Instead, it reframes it. The curvature described by Einstein might be analogous to the pressure or temperature of a fluid, quantities that emerge from deeper microscopic dynamics. If so, then the equations of general relativity could be emergent laws, describing the collective behavior of the underlying structure. This perspective would explain why general relativity works so well at large scales, yet fails at singularities where the microscopic picture becomes dominant. In exploring these phenomena, physicists do not discard the classical picture. They expand it by recognizing that the thermodynamic properties of horizons provide clues about the universe's hidden architecture. These clues invite us to search for the microscopic structure of spacetime and the principles that give rise to gravity. If gravity is emergent, then thermodynamics may be the language through which its true nature reveals itself. The discovery that gravity and thermodynamics are intertwined invites a deeper reflection on how physical laws emerge from microscopic reality. Thermodynamics itself is an example of a framework that describes systems not at the level of individual particles, but at the level of collective behavior. No single molecule carries temperature or pressure. These concepts arise only when vast numbers of molecules interact in ways that smooth out individual irregularities. From this perspective, the connection between gravity and thermodynamics begins to suggest a profound possibility. Perhaps the smooth geometric structure of spacetime behaves like the thermodynamic limit of a deeper microscopic world, and the laws of general relativity are the large-scale rules that emerge when countless underlying degrees of freedom cooperate. To appreciate why this idea holds such power, consider how entropy functions in systems we understand well. Entropy counts the number of microscopic configurations compatible with a given macroscopic state. A gas confined within a box might appear uniform to the eye, yet at the microscopic level, its molecules move in countless ways. The entropy of the gas is a measure of the number of possible molecular arrangements consistent with its temperature and pressure. If a black hole possesses entropy, then it must possess microscopic configurations as well. These configurations cannot be described by the classical geometry of general relativity. They must belong to a deeper level of structure that general relativity does not include. The fact that the entropy of a black hole depends on its surface area rather than its volume suggests that these configurations live on or near the horizon, rather than throughout the interior. This is a radical idea, yet it arises directly from established physical principles. When Hawking calculated the temperature of black holes, he revealed something equally surprising. The temperature arises not from matter inside the black hole, but from quantum fluctuations just outside the horizon. These fluctuations create particle pairs. One falls into the black hole, while the other escapes, producing a flux of radiation that we interpret as the black hole losing mass. This process is subtle and depends on the curvature of spacetime. It demonstrates that quantum fields are deeply sensitive to geometric structure, and that the horizon acts as a kind of thermodynamic surface. The entropy and temperature of a black hole therefore arise not from the classical geometry alone, but from the interplay between geometry and quantum fields. This interplay hints that the classical geometry itself could be emergent. The thermodynamic nature of spacetime becomes even more striking when we consider that horizons can form not only around black holes, but around observers with constant acceleration. An accelerating observer perceives a horizon behind them beyond which events cannot influence their motion. This horizon behaves thermodynamically, producing a temperature proportional to the acceleration. The Unruh effect shows that the presence of heat does not require matter. It can arise from the shape of spacetime and the motion of the observer. This suggests that horizons are not merely geometric boundaries, they are physical objects with thermodynamic properties. These properties provide a window into the microscopic structure of spacetime. Such observations motivate the idea that gravity itself might arise from a tendency toward thermodynamic equilibrium in the underlying degrees of freedom. If spacetime contains microscopic states, and if those states obey statistical laws, then the curvature described by general relativity could be the macroscopic expression of their collective behavior. In this view, Einstein's equations function much like thermodynamic equations. They describe the large-scale behavior of spacetime without revealing the details of the microscopic structure. This perspective is consistent with the fact that general relativity works so well at large scales, yet encounters difficulties at singularities and quantum levels. The theory captures the emergent behavior, but not the fundamental ingredients. Another important clue comes from the behavior of information in gravitational systems. Information plays a critical role in thermodynamics because entropy is closely connected to the number of microscopic states and the amount of information required to specify them. The fact that black hole entropy is proportional to horizon area means that the information stored in a gravitational system scales differently from the information stored in ordinary matter. This scaling suggests that gravitational systems obey a different set of principles. ones that relate geometry to information in unexpected ways. These principles may govern the emergence of spacetime from microscopic processes. The holographic principle offers a striking example of how such principles can operate. According to this idea, the information contained in a region of space is encoded on its boundary. This concept emerged from the study of black hole entropy, but has since been applied more broadly. In certain contexts, such as in negatively curved spaces, a precise mathematical relationship exists between gravity in a higher dimensional spacetime and a quantum theory without gravity defined on its boundary. This relationship shows that gravitational physics can emerge exactly from non-gravitational quantum systems. While this correspondence does not describe our universe directly, it proves that emergent gravity is not merely a conceptual possibility. It is a concrete mathematical reality in specific settings. In light of these discoveries, the picture of gravity as a purely geometric force begins to shift. Geometry itself may be the macroscopic description of something deeper. Just as the smoothness of a fluid disguises the motion of molecules, the smooth curvature of spacetime may disguise the behavior of microscopic degrees of freedom. Thermodynamics becomes the bridge between these layers of reality. It provides clues about the microscopic structure by revealing how macroscopic quantities, such as temperature and entropy, behave. When those quantities appear in gravitational contexts, they signal that gravity and geometry might arise from the same underlying processes that give rise to thermodynamic behavior in other systems. The convergence of gravity and thermodynamics therefore represents more than a surprising coincidence. It is a guide toward the deeper structure of spacetime, the behavior of horizons, the temperature experienced by accelerating observers, and the entropy of black holes all point toward a universe in which geometry is not fundamental, but emergent. If gravity is indeed a thermodynamic effect arising from microscopic processes, then understanding these processes may lead to a unified description of gravity and quantum mechanics. This possibility drives much of the current research in theoretical physics and motivates the search for a deeper understanding of spacetime. The connection between thermodynamics and gravity grows even more compelling when we look closely at how physical systems react to changes in energy, information, and geometry. In ordinary thermodynamics, the behavior of a system depends on the distribution of microscopic states and on how the system moves toward equilibrium. Hot objects cool because energy spreads outward. Gases expand because molecules seek a wider range of possible arrangements. Entropy increases because systems naturally drift toward configurations that are more probable. These principles are simple yet powerful, and they govern everything from boiling water to the evolution of stars. What is remarkable is that gravitational systems, which seem so distant from everyday thermodynamics, exhibit similar tendencies under the surface. One of the clearest examples appears when we consider how horizons respond to matter and energy. If a piece of matter falls into a black hole, the horizon expands. This expansion increases the area and therefore the entropy of the black hole. The process resembles the way ordinary systems absorb heat and increase their entropy when additional energy is introduced. Yet no classical mechanism explains how a geometric surface can behave like a thermodynamic object. The horizon has no atoms, no molecules, no physical structure in the classical sense. It is simply a boundary beyond which information cannot escape. Its thermodynamic behavior therefore must arise from a deeper level of physics, one that endows the horizon with microscopic states, even though the classical description contains none. This insight leads to a broader perspective in which geometry becomes a tool for tracking information. In a sense, space-time curvature tells matter how to move, while entropy tells us how information is organized. If the entropy of a gravitational system depends on horizon area, then the geometry of spacetime plays a direct role in determining how information is stored and distributed. The curvature of spacetime influences the flow of information by determining which regions of the universe can communicate with which others. Horizons emerge wherever communication becomes impossible. These horizons then carry thermodynamic properties, suggesting that information flow and gravitational dynamics are inseparable. The deeper structure of spacetime must therefore encode both geometry and information in a unified way. Further support for this idea comes from considering how energy behaves near horizons. When matter approaches a horizon, the energy as measured by a distant observer becomes increasingly redshifted. This means that from the perspective of the observer, the matter appears to slow down and lose energy as it nears the boundary. The horizon therefore acts like a thermodynamic surface, absorbing energy in a way that mimics the behavior of physical materials. This absorption must reflect the microscopic degrees of freedom associated with the horizon. If the horizon were merely a geometric boundary with no internal structure, it could not absorb energy thermodynamically. The fact that it does absorb energy, and that this absorption changes its entropy, points once again to an underlying statistical picture. Quantum field theory reinforces this picture by showing that the vacuum itself behaves thermodynamically. Virtual particles constantly appear and vanish, contributing to the fluctuations that underlie the Unruh effect and Hawking radiation. These fluctuations depend on the curvature of spacetime and the presence of horizons. The vacuum is not empty, but filled with potential activity that manifests as heat under certain conditions. If the vacuum possesses such properties, then spacetime may function like a medium with microscopic structure. Gravity, in this view, arises not from a fundamental force, but from the way these microscopic elements respond to changes in energy and information. The thermodynamic behavior of spacetime also sheds light on the limits of classical theory. Singularities, where curvature becomes infinite, are places where the classical description loses meaning. In a thermodynamic interpretation, these singularities may represent points where the emergent description breaks down because the underlying microscopic variables no longer behave collectively. Just as a fluid description fails at extremely small scales, where the individuality of molecules becomes important, the classical geometric description fails near singularities, where the underlying structure dominates. This interpretation does not solve the problem of singularities directly, but it provides a conceptual framework in which they are expected features of an emergent theory, rather than fundamental inconsistencies. Another profound implication of the thermodynamic perspective is that Einstein's equations themselves may be emergent. Several researchers have shown that under certain assumptions, the equations of general relativity can be derived from thermodynamic principles. By assuming that entropy is proportional to horizon area and that heat flow across horizons follows the usual thermodynamic rules, one can recover the equations that describe spacetime curvature. This approach does not treat gravity as a force. It treats it as a manifestation of how information and energy distribute themselves in spacetime. The fact that these equations can be derived from thermodynamic principles strongly suggests that they are not fundamental laws, but emergent relations. This insight reframes our understanding of the universe. It suggests that the deep connection between gravity and thermodynamics is not a coincidence, but a reflection of the underlying architecture of reality. Spacetime may not be a smooth geometric fabric, but a large-scale approximation of something more intricate. The microscopic elements that compose it could be informational, quantum mechanical, or something entirely beyond our current imagination. Their collective behavior would then produce both the geometry described by general relativity and the thermodynamic properties revealed by black hole physics. These ideas also reshape our understanding of where to search for a quantum theory of gravity. Instead of attempting to quantize spacetime directly, it may be necessary to identify the microscopic degrees of freedom from which spacetime emerges. This shift in perspective aligns gravity with other emergent phenomena in physics. Just as fluid dynamics cannot be derived by quantizing the equations of hydrodynamics, a true quantum theory of gravity may not arise from quantizing Einstein's equations. Instead, it must arise from identifying the fundamental building blocks whose collective behavior produces geometry and thermodynamics. The convergence of thermodynamics and gravity therefore opens a path toward understanding the deeper nature of space-time. It does not replace classical gravity, but enriches it, revealing that the smooth geometry we observe is the surface of a far more complex and fascinating reality. The hints provided by horizon thermodynamics, quantum field behavior, and information theory all point toward a universe where gravity may be a thermodynamic effect arising from microscopic processes. This perspective does not claim to reveal the ultimate truth. It offers a direction, a set of clues that guide us toward the hidden structure underlying the cosmos. The universe has always invited us to imagine what lies beyond the visible. But the discovery that information itself might shape the structure of space-time is one of the most profound insights in modern physics. This insight did not emerge from speculation. It arose from the stubborn, unavoidable facts uncovered through the study of black holes and quantum theory. The peculiar behavior of black hole entropy, scaling with the area rather than the volume of the region, challenged every expectation built from ordinary matter. It suggested that the degrees of freedom describing a gravitational system might reside not within the region itself, but on its boundary. This strange result became the seed of an idea that would grow into the holographic principle, a principle that forever altered the way physicists think about geometry, information, and the nature of reality. To understand how revolutionary this idea is, imagine a familiar physical system, such as a gas confined inside a room. The number of possible microscopic configurations depends on the volume of the room. More volume means more room for molecules to move and more possible arrangements, which in turn means greater entropy. But a black hole does not behave this way. Its entropy is not proportional to the volume enclosed by the horizon. Instead, it is proportional to the area of the horizon measured in Planck units. This means that doubling the radius of a black hole does not simply increase its entropy eightfold, as volume scaling would suggest. Instead, the entropy grows only by a factor of 4. This area scaling is not a mathematical curiosity. It is a precise physical requirement derived from quantum field theory and general relativity. It establishes a limit on the amount of information that can be stored in a region of space-time, and that limit depends on surface area rather than volume. This discovery leads to a startling conclusion. If the information content of a region is determined by its boundary, then the region behaves as if its three-dimensional physics is encoded on a two-dimensional surface. This idea is reminiscent of a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image. In a similar way, the holographic principle proposes that the geometry and physical processes inside a region of space-time can be described by information encoded on its boundary. This principle emerged from the study of black holes, but soon grew into a more general statement about the nature of the universe. The holographic principle implies that the volume of space we experience may not be fundamental. Instead, it may be a representation of information stored on a lower dimensional structure. This does not mean that the world is an illusion. It means that the underlying description of reality may have fewer dimensions than the world we perceive. The extra dimensions of space-time emerge from the organization of the information encoded on the boundary. This idea gained strong support from developments in string theory, where researchers discovered that certain gravitational theories in higher dimensional spaces are exactly equivalent to quantum theories without gravity defined on lower dimensional boundaries. One of the most striking realizations came from the study of spaces with constant negative curvature, where a precise mathematical relationship was found between a gravitational theory in a higher dimensional space-time and a quantum field theory without gravity defined on its boundary. This relationship is known in research as ADS-CFT. It demonstrates that the physics inside a region, including gravity, curvature, and space-time structure, can be fully described by a theory without gravity living on the boundary. This correspondence is exact in the settings where it applies. It shows that gravity can emerge from underlying quantum information. The geometry of space-time appears not as a fundamental entity, but as a property that arises from the dynamics of the boundary theory. Although our universe does not share the exact geometry required for ADS-CFT, the correspondence proves a crucial point. It shows that gravity can emerge from non-gravitational physics. It reveals that geometry can arise from the organization of quantum information. And it demonstrates that the holographic principle is more than a conceptual idea. It is a precise mathematical framework that operates within certain conditions. These discoveries transform the way physicists understand the relationship between geometry and information. They suggest that space-time itself may be a collective phenomenon produced by interactions at the boundary. The holographic principle also clarifies why black hole entropy follows an area law. If the degrees of freedom that describe the interior reside on the boundary, then the entropy should scale with the boundary area. The principle also explains why information cannot be stored independently at every point in the volume. Doing so would violate the maximum entropy allowed by the area bound. Instead, the universe appears to limit information storage in a way that ties geometry and thermodynamics together. These limits suggest that space-time is not an arbitrary geometric landscape, but a structure shaped by information capacity. The principle also reshapes how physicists think about locality. In classical physics, events are local. They occur at specific points in space and time. But if the true degrees of freedom are encoded on a boundary, then locality in the bulk may be an emergent property. The apparent separation of events in three-dimensional space may arise from the organization of information in lower dimensions. This idea challenges intuition, but remains consistent with everything we know about holographic systems. The holographic principle provides a bridge between quantum mechanics and gravity by showing how geometry can emerge from quantum information. It reveals that the tension between general relativity and quantum theory may be resolved not by forcing them to merge within the same framework, but by understanding that both arise from deeper informational rules. In this view, gravity is not a fundamental force, but a large-scale expression of how information arranges itself. The geometry of space-time emerges from the entanglement patterns of underlying quantum states. The holographic principle reshapes our understanding of space by suggesting that the richness of a three-dimensional world may arise from information stored on a lower dimensional surface. This idea is unsettling at first, because it contradicts the intuition that space is built from independent volume elements stacked together like the bricks of a structure. Instead, it presents a world in which the fundamental description resides not in the volume, but on the boundary. The interior then becomes a representation of boundary information in a way that resembles how a hologram uses a two-dimensional plate to create a three-dimensional image. Yet unlike an optical hologram, the holographic principle is not a metaphor. It emerges directly from the way black hole entropy behaves and from the precise mathematical properties of quantum fields in curved space-time. To see why the principle carries such weight, consider what would happen if the entropy of a region of space scaled with volume. In that case, we could pack information into arbitrarily small regions, increasing it without bound as the system becomes denser. This would contradict the existence of a maximum entropy for black holes. If a region of space contained more entropy than a black hole of the same size, then collapsing that region would produce a black hole with less entropy than the matter originally contained. This would violate the second law of thermodynamics, which forbids entropy from decreasing. The only way to avoid this contradiction is for entropy in gravitational systems to scale with area, not volume. This requirement forces the universe to obey a principle that limits how much information can be stored in any region of space. The holographic principle emerges naturally from this constraint. This realization has profound implications for the nature of space-time. It suggests that the fabric of space is not a fundamental entity, but a manifestation of information storage. The geometry of a region, including its curvature, volume, and connectivity, must reflect the underlying informational rules that govern how much entropy can be stored within it. These rules are not arbitrary. They arise from quantum mechanics and general relativity working together at the boundary. If the interior of a region behaves like a holographic representation, then geometry itself must emerge from how information is arranged on the boundary. The ADS-CFT correspondence provides a concrete demonstration of how this emergence occurs. In the gravitational theory, the interior of the spacetime contains curvature that responds to mass and energy. In the boundary theory, there is no gravity at all. Instead, there is a quantum field theory with specific properties. The remarkable discovery is that the equations governing the quantum field theory reproduce the structure of the gravitational interior. Correlation functions in the boundary theory map directly to geometric features in the bulk. Distances, areas, and even entire shapes of the curved spacetime arise from patterns of entanglement in the boundary. This mapping is not approximate. It is exact within the conditions where the correspondence applies. The correspondence also shows that the entanglement of boundary states determines the connectivity of the bulk spacetime. Highly entangled states correspond to smooth geometric regions, while reducing entanglement can cause the interior geometry to shrink or fragment. This idea has led to the suggestion that spacetime may be woven from entanglement, that the threads connecting regions of space are made not of physical material, but of quantum correlations. This perspective further supports the idea that geometry is emergent rather than fundamental. It depends on the organization of information, not on any underlying geometric substance. One of the deepest implications of the holographic principle is that locality may not be fundamental. In classical physics, events occur at specific points and influence each other according to well-defined rules. But if the true description of a region resides on its boundary, then the apparent locality of events in the interior may arise from the way information is encoded. 2 points that seem distant in the bulk spacetime could correspond to degrees of freedom that are adjacent on the boundary. The geometric separation we experience may therefore be a large-scale effect, not a fundamental property. This does not imply that locality is false. It means that locality is emergent, arising from deeper informational principles. The holographic principle also offers a possible solution to the information paradox. If information about matter falling into a black hole is stored on the horizon, then it need not be lost when the black hole evaporates. The horizon acts as a repository of information, encoding the microscopic states that represent the black hole's entropy. When the black hole radiates, the outgoing radiation can carry information away in a subtle way that preserves the fundamental rules of quantum mechanics. This perspective transforms the paradox from a conflict between relativity and quantum theory into an insight about how information behaves in a holographic universe. Another important consequence of the holographic principle is that the interior of a region can be reconstructed entirely from boundary data. This idea, known as bulk reconstruction, shows that every point in the interior corresponds to a specific pattern of information on the boundary. The reconstruction works even for regions hidden behind horizons, revealing that the interior of a black hole might be encoded on its surface. Although these reconstructions are established only in certain theoretical settings, they demonstrate that the interior of spacetime is not an independent entity. It is a representation of boundary information. These developments suggest that gravity is not simply a property of spacetime. It is a manifestation of how information organizes itself. The laws of gravity emerge from the thermodynamics of horizons and from the entanglement structure of quantum states. The curvature that guides the motion of planets and light arises from informational constraints rather than from a fundamental field. This view integrates thermodynamics, quantum mechanics, and general relativity into a coherent framework, revealing that the universe may be governed by informational principles at its deepest levels. The holographic principle, therefore, stands as a cornerstone of modern theoretical physics. It provides a powerful lens through which to interpret the behavior of gravitational systems and offers a path toward unifying gravity with quantum mechanics. By understanding how information defines geometry, physicists gain insight into the potential microscopic structure of spacetime. This insight leads naturally to the question of how ideas like entropic gravity emerge from these principles, and how they attempt to describe the force we attribute to gravity as a thermodynamic effect. The realization that geometry may emerge from information invites a new way of imagining the universe, one in which the familiar structure of space is not built from continuous points, but from relationships encoded in a deeper substrate. This perspective becomes clearer when we examine how the holographic principle reshapes the meaning of distance, area, and curvature. In a holographic world, the geometry we observe is not something that exists independently. It is the macroscopic expression of entanglement patterns and information flow. This interpretation does not weaken the classical picture. It enriches it, revealing that the smooth curvature described by general relativity may be the visible surface of an invisible architecture defined by quantum information. One of the most revealing ideas to emerge from holographic thinking is the way entanglement determines the shape of spacetime. When two regions of a boundary theory are highly entangled, the corresponding points in the bulk become connected by a smooth geometric bridge. When entanglement is reduced, the bridge can narrow or even disconnect, altering the bulk geometry. This idea provides a mechanism by which space-time connectivity could arise from entanglement patterns alone. It suggests that the distances we measure in the bulk reflect the strength of correlations in the underlying structure, and that the emergence of spatial regions depends on how information is shared between the degrees of freedom on the boundary. Understanding space-time in these terms helps explain why gravity behaves so differently from other forces. Electromagnetism and the nuclear forces operate within the framework of quantum field theory, where particles and interactions arise from quantizable fields. Gravity, however, resists quantization in any straightforward way, as if it does not fit naturally into the category of fundamental forces. The holographic principle offers an explanation. Gravity is the large-scale behavior of the emergent geometry, not a fundamental interaction. Attempts to quantize gravity directly may fail because they try to quantize something that is not fundamental. Instead, the true quantum description resides in the degrees of freedom that generate the geometry through their entanglement structure. The holographic principle also clarifies the deep relationship between entropy and area. If the degrees of freedom of a gravitational system are encoded on a boundary, then the maximum entropy of the system should scale with the size of that boundary. This matches the behavior of black holes, whose entropy depends on the horizon area. The principle therefore unifies the thermodynamic behavior of black holes with the informational structure underlying spacetime. It reveals that the area law is not an accident, but a reflection of the limits imposed by the underlying quantum theory. These limits ensure that the universe cannot store information arbitrarily densely without collapsing into a black hole, and they prevent violations of thermodynamic principles. Another intriguing implication of the holographic principle concerns the nature of horizons. Horizons arise whenever information becomes inaccessible to an observer, whether because of gravitational collapse, acceleration, or cosmic expansion. The thermodynamic properties of horizons suggest that they act as surfaces where information becomes encoded. In a holographic universe, the horizon is not merely a geometric boundary, but a repository of microscopic degrees of freedom. These degrees of freedom determine the entropy of the black hole, the temperature experienced by an accelerating observer, and the information content of a region of space. The horizon becomes the interface between the emergent geometry and the underlying information. The idea that horizons contain the information necessary to reconstruct the bulk has profound implications for the behavior of space and time. It suggests that the information stored on the boundary could determine everything that happens in the interior, from the motion of particles to the evolution of fields. The bulk becomes a representation, a geometric reflection of the boundary data. This perspective aligns naturally with the observation that the equations of general relativity can be derived from thermodynamic principles. If geometry itself is emergent, then the laws governing that geometry must also be emergent. They arise from the statistical behavior of the microscopic degrees of freedom encoded on the boundary. This approach deepens our understanding of why black hole evaporation does not necessarily destroy information. If the information is encoded on the horizon, then as the black hole radiates, the outgoing particles can carry away that information in subtle correlations. The evaporation process becomes a transfer of information from the horizon to the radiation field rather than a destruction of information. This interpretation preserves the principles of quantum mechanics while respecting the geometric behavior described by general relativity. The holographic framework thus provides a potential path toward resolving one of the most famous paradoxes in physics. The holographic principle also extends beyond black holes, offering insights into the nature of cosmology. If the universe itself follows holographic rules, then the large-scale structure of spacetime may be determined by information encoded on a cosmic boundary. This idea remains speculative, but it offers a unifying perspective in which gravity, thermodynamics, and quantum mechanics arise from a single underlying principle: the organization of information. Whether or not the universe is holographic in a strict sense, the principle provides a powerful tool for exploring the nature of space and time. At its core, the holographic principle tells us that geometry is not primary. It is a macroscopic description that emerges from the way information is stored and shared. This view aligns perfectly with the hints provided by black hole thermodynamics, quantum field theory, and the Unruh effect. It offers a coherent framework in which the thermodynamic behavior of gravity arises from the underlying informational structure, and it provides a foundation for theories like entropic gravity, which propose that gravitational attraction may be a consequence of statistical tendencies in the microscopic degrees of freedom that compose spacetime. The holographic perspective does not claim to reveal the full nature of the universe, but it opens a path toward understanding why gravity behaves as it does and how geometry might emerge from something deeper. It challenges our intuition about space and time while remaining grounded in precise mathematical relationships. By revealing that information defines geometry, the holographic principle reshapes our understanding of gravity and illuminates the hidden structure that may lie beneath the world we see. Gravity has long been treated as a fundamental feature of the universe, a basic interaction woven into the structure of spacetime itself. Yet the clues revealed by thermodynamics and holography have encouraged physicists to consider a different possibility, one in which gravity may arise from statistical tendencies built into the microscopic architecture of the cosmos. Among the most influential attempts to articulate this possibility is the proposal introduced by Verlinde in the year 2010, in which he argued that gravity might be understood not as a fundamental force, but as an entropic effect. His idea sparked immediate interest because it offered a way to connect gravitational behavior with the thermodynamic and informational properties of spacetime. Verlinde did not attempt to modify general relativity directly. Instead, he sought to reinterpret the origin of gravitational interactions by examining them through the lens of entropy, information, and the microscopic degrees of freedom suggested by the holographic principle. To understand the reasoning behind Verlinde's proposal, it is helpful to recall the thermodynamic insights that motivated it. When a system has entropy, it possesses microscopic degrees of freedom that encode information about its possible states. Forces that appear at macroscopic scales can sometimes be understood as tendencies of systems to maximize entropy. A familiar example is the entropic force that arises when a polymer molecule in a solution resists being stretched. The molecule is not pulled by any fundamental interaction. Instead, it tends to return to a coiled state because that configuration allows more microscopic arrangements and therefore more entropy. Verlinde wondered whether gravity, too, might arise from such entropic tendencies, not from a fundamental exchange of particles or a quantum field, but from the statistical behavior of underlying informational degrees of freedom. His starting point was remarkably simple. If information about matter is stored in microscopic degrees of freedom associated with surfaces such as horizons, and if the distribution of matter changes,
then the entropy associated with those surfaces should also change. A system with changing entropy experiences a tendency toward configurations that increase entropy. Verlinde proposed that what we perceive as gravitational attraction may be precisely this entropic tendency. When a particle approaches a region that contains more microscopic degrees of freedom, the increase in entropy produces an effective force. This force is not fundamental. It arises from the statistical behavior of the underlying information. By combining this idea with the relationship between entropy and area, suggested by the holographic principle, Verlinde showed that one can recover the familiar form of Newton's gravitational law. The reasoning is subtle, but grounded in established physical principles. Verlinde considered a hypothetical surface surrounding a mass, a surface that stores information about the interior in a way reminiscent of holographic ideas. If a test particle moves relative to the surface, the entropy associated with that surface changes. Using the thermodynamic relation that connects force to entropy and temperature, he demonstrated that the resulting entropic interaction takes the form of an inverse square law. This was not a derivation from fundamental quantum fields. It was an argument showing that Newton's law could emerge naturally if spacetime possesses microscopic degrees of freedom that follow thermodynamic rules. Verlinde pushed this idea further by examining how spacetime geometry might arise from information. If changes in entropy correspond to changes in gravity, then the geometric curvature described by general relativity might itself be an emergent property. Gravity would not bend spacetime. Instead, spacetime would appear curved because the underlying information is distributed in a particular way. The geodesic motion of objects would reflect the statistical equilibrium of microscopic degrees of freedom rather than the action of a fundamental force. This interpretation does not alter the observable predictions of general relativity. It reinterprets them, suggesting that curvature is not a basic feature of the universe, but a macroscopic effect produced by deeper physics. One of the appealing aspects of Verlinde's approach is that it aligns with the idea that the surface area of a region encodes the information required to describe it. If the information content of spacetime is stored holographically, then gravitational effects might emerge naturally from how this information behaves. Verlinde's proposal does not claim to reveal the exact microscopic degrees of freedom. Instead, it treats their existence as implied by black hole thermodynamics and holography. The entropic interpretation provides a conceptual bridge between the thermodynamic behavior of horizons and the classical description of gravity. However, Verlinde emphasized that his argument should not be mistaken for a completed theory. He did not propose a new set of field equations or a replacement for general relativity. Instead, he offered a new perspective on why gravity takes the form it does. His aim was to show that gravity might be emergent rather than fundamental, and that the familiar inverse square law could be understood from entropic considerations. This conceptual shift sparked widespread discussion because it provided a potential path toward unifying gravitational physics with the thermodynamic and informational insights discovered in other areas of research. The idea that gravity could be entropic remains controversial, but it is grounded in established physics rather than speculation. Verlinde's derivation uses only known thermodynamic relations, holographic scaling, and simple assumptions about how information might behave in spacetime. It does not introduce new forces or exotic matter. Instead, it challenges the way we think about gravity by suggesting that its familiar behavior arises from deeper statistical rules. The success of this approach depends on whether future theories can identify the microscopic degrees of freedom responsible for gravitational behavior and show how spacetime geometry emerges from them. Verlinde's proposal gained attention not because it replaced established theory, but because it reframed gravity in a language that connected several powerful ideas. Thermodynamics, holography, and information theory all pointed toward a universe in which geometry might emerge from microscopic structure. Verlinde sought to show that gravitational attraction could arise from the behavior of this structure without invoking a fundamental gravitational field. To appreciate the depth of his argument, it is necessary to examine how he connected entropy, information, and motion in ways that echo known physical phenomena while offering a new lens through which to view gravity. A central element of his reasoning involves the relationship between entropy and force. In thermodynamics, when the entropy of a system depends on the position of a particle, a force arises that pushes the system towards states of higher entropy. This force does not require a physical field. It emerges naturally from statistical tendencies. Verlinde applied this principle to spacetime by imagining that information about matter is stored on surfaces surrounding that matter. If a particle moves closer to such a surface, the number of microscopic configurations available to the system changes. The entropy associated with the configuration increases or decreases depending on the direction of motion. The tendency of entropy to increase then produces an effective force whose magnitude depends on how rapidly the entropy changes with position. To illustrate this idea, Verlinde introduced a simple model in which a particle approaches a surface endowed with a certain number of bits of information. He assumed that the entropy associated with the surface increases by a small amount when the particle moves closer. By applying the thermodynamic relation that connects force to entropy and temperature, he found that the resulting force depends inversely on the square of the distance between the particle and the mass enclosed by the surface. This is the same scaling found in Newton's law of gravitation. It suggests that gravity might arise not because masses emit a field, but because the microscopic information stored on surfaces responds statistically to the presence of matter and tends to reach states of higher entropy. Verlinde also explored how his entropic framework could reproduce aspects of general relativity. Instead of treating spacetime as a smooth geometric entity, he imagined that it arises from the distribution of information in a manner consistent with the holographic principle. In this view, the curvature of spacetime is not a primitive concept. It is a manifestation of how the microscopic degrees of freedom are organized. When matter is present, it changes the distribution of information on surrounding surfaces. This change in information leads to an emergent geometry that objects follow in their motion. The geodesic paths described by Einstein's equations become statistical equilibrium paths rather than consequences of fundamental curvature. One of the appealing features of entropic gravity is its conceptual connection to horizon thermodynamics. Horizons possess entropy proportional to their area, and they exhibit temperature due to quantum effects. These properties strongly suggest that horizons contain microscopic degrees of freedom. Verlinde's proposal treats these degrees of freedom not as special features of black holes, but as general characteristics of spacetime. In his picture, the information content associated with a surface depends on its area, consistent with the holographic principle. The entropic force described in his work arises from changes in this information content as matter moves. Verlinde also noted that the emergence of gravity from entropic principles aligns with the idea that spacetime itself might be emergent. If spacetime geometry arises from the statistical organization of microscopic degrees of freedom, then gravity must also be emergent. The smoothness of spacetime, the curvature described by general relativity, and the structure of gravitational interactions would all arise from deeper processes. This perspective explains why attempts to quantize gravity directly encounter difficulties. If gravity is not fundamental, then quantizing it would be like quantizing the equations of fluid dynamics. One would be quantizing an emergent phenomenon rather than the true microscopic constituents. The entropic framework also offers a way to interpret inertia. In classical physics, inertia is the tendency of an object to resist changes in its motion. Verlinde argued that inertia too might have informational origins. If the motion of an object changes the distribution of information on surrounding surfaces, then the object may experience an entropic response that manifests as inertia. This idea is speculative but consistent with the broader theme that spacetime dynamics may be deeply intertwined with informational structure. While Verlinde's reasoning is grounded in established thermodynamic principles, it does not provide a detailed description of the microscopic degrees of freedom responsible for gravitational behavior. It offers a framework rather than a complete theory. The success of this framework depends on whether future research can identify the underlying informational elements and show how they give rise to spacetime and gravity. This challenge remains open, but the conceptual clarity of extending thermodynamic reasoning to gravity has made entropic gravity an influential idea in the search for the deeper nature of spacetime. A further appeal of Verlinde's proposal lies in its potential to unify several insights that arise from different areas of physics. Black hole entropy, holographic limits, and the thermodynamics of horizons all point toward a universe in which information plays a central role. Verlinde's argument fits naturally within this picture, providing a way to interpret gravitational attraction as a statistical effect. Even if the specific details of his model are refined or replaced in future work, the underlying idea that gravity might emerge from information has shaped the conversation in theoretical physics. Verlinde's proposal drew particular attention, not only because it reproduced Newton's law in an unexpected way, but also because it invited physicists to reconsider the foundations of gravity with unusual clarity. If gravity arises from informational tendencies, then many features of spacetime that once appeared fundamental become signs of deeper structure. The familiar curvature described by general relativity would not be the starting point of physics, but the large-scale limit of microscopic interactions whose true nature remains hidden. This shift in perspective is subtle but powerful. It turns gravity into a phenomenon that emerges only when countless underlying degrees of freedom work together, much like temperature emerges from molecular motion. The challenge is to understand what these degrees of freedom are and how they generate the geometry we observe. One of the most intriguing aspects of Verlinde's approach is how it aligns with the holographic principle. If information about matter is stored holographically on surfaces, then gravitational interactions must reflect the behavior of that information. In Verlinde's picture, when matter moves, it alters the informational structure on surrounding surfaces. These alterations manifest as tendencies towards states of maximal entropy. The resulting entropic force has the form of Newton's law, showing that gravity could emerge naturally from holographic storage of information. The elegance of this result lies in the way it brings together thermodynamics, holography, and classical gravitational behavior. It suggests that the geometry Einstein described may be one expression of a deeper informational reality. Verlinde extended his ideas beyond the simple derivation of Newton's law by exploring how large-scale gravitational behavior might deviate from classical expectations in certain regimes. If gravity is emergent, then the entropic tendencies governing it may change depending on how information is distributed in the universe. This idea led him to propose a new interpretation of phenomena, usually attributed to dark matter. Instead of treating dark matter as an unseen form of mass, Verlinde suggested that deviations from Newtonian behavior could arise from changes in the entropic structure of spacetime on galactic scales. These deviations would appear as extra gravitational influence even in regions where little visible matter exists. Although this idea generated significant interest, it remains controversial because observational evidence strongly supports the presence of dark matter, particularly at the scale of galaxy clusters and the cosmic microwave background. Verlinde's interpretation offers an alternative perspective, but does not match the full range of observations. Even so, Verlinde's work stimulated research into how entropic principles might influence gravitational behavior across different scales. His framework opened the possibility that gravity could vary depending on how information is distributed rather than on the presence of unseen matter. This approach motivated studies that tested his predictions against astronomical data. Some of these tests showed qualitative agreement on galactic scales, while others revealed significant discrepancies. These results highlight the need for caution. The entropic interpretation offers insights, but does not yet replace the standard model of cosmology. It may contribute to understanding gravitational behavior, but it does not capture the full complexity revealed by observations. The value of Verlinde's proposal lies not in its completeness, but in the direction it points. It encourages physicists to explore how information, entropy, and microscopic structure might generate gravitational behavior. It shifts attention away from traditional attempts to quantize gravity directly and toward identifying the deeper processes from which gravity might emerge. This shift mirrors the way scientists approach other emergent phenomena. One does not quantize fluid dynamics to understand water. One studies the molecules. Similarly, if gravity is emergent, one must study the informational degrees of freedom that produce spacetime geometry. Another element that strengthens the plausibility of entropic gravity is the connection between entropy and surface area. This area dependence appears in black hole thermodynamics and in the holographic principle. If information is stored on surfaces, then changes in matter distribution must produce changes in the entropy of those surfaces. These changes naturally lead to entropic forces. Gravity becomes the macroscopic expression of these forces, not a fundamental interaction. This interpretation aligns with the idea that the universe has a maximum information capacity determined by the size of surfaces rather than volumes. It also complements the observation that horizons behave thermodynamically, possessing temperature and entropy even when no matter is present. Despite these appealing connections, Verlinde's model remains incomplete. It does not specify the exact microscopic variables responsible for the entropy changes. It does not provide a full set of equations equivalent to Einstein's theory. And it does not reproduce all observed gravitational phenomena. What it does offer is a conceptual framework that fits naturally with the thermodynamic and holographic insights revealed by modern physics. It shows that gravity can be interpreted as a statistical effect arising from information, and that the familiar laws of gravitational attraction can emerge from thermodynamic principles. This framework invites physicists to search for the microscopic structure of spacetime rather than to treat geometry as fundamental. It suggests that the roles of entropy, information, and quantum mechanics are central to the emergence of gravity. It provides a lens through which the behavior of horizons, the scaling of entropy, and the challenges of unifying quantum mechanics and general relativity might be understood as reflections of deeper informational processes. Verlinde's proposal does not claim to answer every question. Instead, it reframes the questions themselves. It asks why gravity should be fundamental when so many of its properties resemble those of emergent quantities. It challenges us to consider whether space-time, geometry, and gravitational attraction may arise from microscopic informational interactions. These questions guide the search for a more complete theory that unifies thermodynamics, quantum mechanics, and geometry. The possibility that gravity might emerge from microscopic processes invites curiosity, but scientific exploration demands more than conceptual beauty. It requires comparison with observation, confrontation with data, and the careful examination of whether new ideas can match the precision with which established theories describe the universe. Verlinde's entropic gravity enters this arena with an intriguing promise, yet it must operate under the same constraints that govern every scientific proposal. Gravity is one of the most thoroughly tested aspects of physics, and any theory that seeks to reinterpret or extend it must reproduce those tests with exceptional accuracy. This chapter examines how entropic gravity fares when placed under the scrutiny of experimental and observational evidence, and how it stands in the face of theoretical criticism from the broader physics community. One of the first challenges for any emergent model is reproducing the success of Newton's law and general relativity across a vast range of scales. These classical frameworks describe the motions of planets, the behavior of falling objects, the bending of light, the precession of orbits, and the propagation of gravitational waves. Their predictions match observation with astonishing precision. This precision sets an extremely high bar. A theory that treats gravity as an entropic phenomenon must recover all these results in appropriate limits. Verlinde's original work reproduced Newton's inverse square law through thermodynamic arguments, suggesting that emergent behavior could yield familiar gravitational interactions. But deriving an equation is not the same as demonstrating a complete correspondence with all known tests, especially those requiring the full machinery of general relativity. The challenge becomes more evident when we consider relativistic phenomena. General relativity predicts that time flows differently in gravitational fields, that light bends around massive objects, and that space-time curves in response to energy and momentum. These predictions have been verified repeatedly through experiments and astronomical observations. An entropic theory must reproduce not only the magnitude of these effects, but also their precise form. Verlinde's proposal provides conceptual insights into how space-time curvature might emerge, but it does not offer a complete set of equations that can be applied to strong gravitational fields or rapidly varying geometries. Without such equations, it cannot yet match the predictive power of general relativity in all regimes. Another challenge arises from the study of galaxy rotation curves, a key area where Verlinde attempted to demonstrate an advantage for emergent gravity. Observations reveal that stars in galaxies orbit faster than expected based on visible matter alone. The classical solution introduces dark matter, an invisible component that exerts gravitational influence. This idea has strong support because it explains not only galaxy rotation curves but also gravitational lensing patterns, the large-scale structure of the universe, and the anisotropies of the cosmic microwave background. Verlinde proposed that deviations from Newtonian behavior could arise from changes in the entropic structure of spacetime at large distances. His interpretation suggested that the additional gravitational pull attributed to dark matter might instead result from the way information is distributed on cosmological scales. To test this idea, researchers compared Verlinde's predictions with observed galaxy data. In some cases, his model produced rotation curves that resembled observations, offering a tantalizing suggestion that entropic effects might account for certain features without invoking dark matter. However, when applied more broadly, the model faced significant limitations. It struggled to match the diversity of galactic behavior across different mass ranges, and it did not reproduce gravitational lensing patterns with the same accuracy as dark matter models. The greatest challenge came from galaxy clusters, where the discrepancy between visible matter and gravitational effects is far larger than in individual galaxies. Verlinde's framework could not account for these discrepancies without additional assumptions, which weakened its explanatory power. The cosmic microwave background adds another layer of difficulty. The fine structure of its temperature fluctuations provides a detailed map of the universe's density and expansion history. These fluctuations depend sensitively on the amount and distribution of dark matter. The standard cosmological model, which includes dark matter and dark energy, fits this data with remarkable precision. Emergent gravity models have not yet produced predictions that match this level of accuracy. Without such correspondence, they cannot replace the dominant cosmological framework. These observational challenges do not invalidate Verlinde's work. They highlight the difference between a conceptual framework and a full physical theory. Entropic gravity offers a new way to think about gravitational interactions, but it has not yet achieved the predictive completeness required to replace general relativity or the dark matter paradigm. Its strength lies in its conceptual unification of thermodynamics, holography, and gravitational phenomena. Its limitation lies in its incompleteness as a quantitative theory. Theoretical criticism also plays an important role in evaluating emergent gravity. Some physicists argue that Verlinde's derivation relies on assumptions that lack clear justification. The identification of entropy with information bits on hypothetical surfaces, while consistent with holographic ideas, requires a more precise microscopic model. Others note that the use of thermodynamic relations in gravitational contexts must be grounded in specific definitions of temperature and entropy, which may not generalize cleanly to all situations. Without a rigorous account of the underlying degrees of freedom, entropic gravity risks depending on analogies rather than fundamental principles. Another concern arises from the fact that Verlinde's argument recovers Newton's law, but not the full relativistic structure of Einstein's equations. General relativity follows from the requirement that physical laws be coordinate independent, and that energy and momentum produce curvature in a specific way. Emergent gravity must replicate this structure with equal rigor. While Verlinde's idea suggests how geometry might arise, it does not yet provide the mathematical system necessary to guarantee consistency across all frames of reference and all gravitational regimes. Despite these criticisms, the entropic approach remains valuable because it opens a path toward understanding why gravity exhibits thermodynamic features. It encourages researchers to examine the microscopic structure of spacetime and to investigate how information flow might give rise to geometry. The limitations of the current framework do not weaken its conceptual importance. They highlight the need for further development, deeper mathematical structure, and empirical testing. The interplay between thermodynamics, information, and geometry remains one of the most promising avenues for exploring the foundations of gravity. One of the most illuminating aspects of the debate surrounding entropic gravity is how it highlights the extraordinary precision with which gravitational physics has been measured. Any alternative theory must operate within this environment of exactness. The classical tests of general relativity, for example, are not vague confirmations. They are measured to extraordinary accuracy. The precession of Mercury's orbit matches Einstein's prediction within the limits of instrumental precision. The bending of light observed during solar eclipses and later through advanced telescopes aligns with calculated values. Time dilation effects observed in atomic clocks on airplanes match theoretical expectations to many decimal places. The orbital decay of binary pulsars due to gravitational wave emission matches predictions from general relativity with astonishing accuracy. These tests place severe constraints on any emergent model. For entropic gravity to succeed, it must not only reproduce these results, but explain them with equal clarity. Another domain in which constraints become especially severe is gravitational lensing. When massive objects lie between a distant light source and Earth, they bend the path of light, producing arcs, distortions, and sometimes multiple images of the same source. General relativity predicts these effects with quantitative precision. Dark matter models, when combined with general relativity, explain lensing patterns on galactic and cluster scales in a way that matches observational data. Entropic gravity must do more than approximate these results. It must reproduce the exact lensing patterns in varied environments. Early analyses of Verlinde's ideas showed partial agreement on galactic scales, but significant disagreements when extended to more complex systems such as galaxy clusters. The lensing produced by the bullet cluster, a well-known example where ordinary matter and gravitational effects are spatially separated, remains especially difficult for emergent gravity frameworks to reproduce without invoking additional structure. This limitation does not disprove entropic ideas. It simply illustrates the precision required to compete with established models. Another crucial constraint comes from the large-scale structure of the universe. Over billions of years, small density fluctuations in the early universe grew into galaxies, clusters, and cosmic filaments. This growth is sensitive to the amount of dark matter because dark matter began to clump long before ordinary matter could cool and collapse. Standard cosmology, built from general relativity and dark matter, reproduces this structure remarkably well. Computer simulations incorporating dark matter generate cosmic webs that match the observed distribution of galaxies. Emergent gravity, in its current form, does not naturally reproduce this structure. Without a detailed mechanism for how information and entropy behave during cosmic evolution, the framework cannot yet describe the formation of large-scale structures with the precision necessary for a complete cosmological model. Even more demanding is the evidence from the cosmic microwave background. The tiny temperature variations across the sky reflect sound waves that propagated through the early universe. These variations depend on the amount of dark matter the density of ordinary matter, and the expansion rate of the universe. The Standard Model fits these measurements with extraordinary accuracy, matching the observed power spectrum across many scales. Any model that seeks to replace dark matter must reproduce this spectrum with similar precision. Entropic gravity has not yet achieved this. While some attempts have been made to explore how emergent behavior might influence cosmic evolution, these studies remain preliminary and lack the predictive power of standard cosmology. Criticism also arises from the theoretical side, particularly regarding the assumptions embedded in Verlinde's derivation. His use of informational surfaces recalls holographic ideas but lacks a full microscopic justification. What are the degrees of freedom stored on these surfaces? How do they interact? What rules govern their dynamics? Without answers to these questions, the entropic picture remains incomplete. It offers hints, but not a complete microscopic theory. The analogy with entropic forces in polymers provides insight, but cannot substitute for a fundamental description. Critics argue that without identifying the true degrees of freedom and demonstrating how geometry arises from them in detail, Verlinde's framework rests on conceptual scaffolding rather than fully developed structure. Another difficulty lies in extending the arguments to relativistic regimes. Deriving Newton's law from entropic considerations provides an interesting insight, but general relativity is far richer and more complex. It requires a consistent set of equations that describe how curvature responds to energy and momentum in dynamic situations, including gravitational waves, black hole mergers, and rapidly changing fields. Entropic gravity has not yet produced a set of equations that can replace Einstein's field equations in such circumstances. Without this, the framework cannot be applied confidently to strong gravitational regimes where general relativity has been tested and confirmed. Despite these limitations, entropic gravity remains valuable because it emphasizes the thermodynamic and informational aspects of gravitational systems. It provides a way to interpret the behavior of horizons, the scaling of entropy, and the links between geometry and information. Even critics acknowledge that the entropic perspective brings conceptual clarity to certain aspects of gravitational physics. It encourages the search for underlying microscopic degrees of freedom and suggests that the path to understanding gravity may lie in identifying how space-time geometry emerges from deeper processes. The incomplete nature of entropic gravity does not diminish the significance of its core idea. It highlights the frontier where conceptual exploration must meet mathematical and observational rigor. The scientific method thrives on such challenges. Theories are strengthened not by agreement alone, but by the process of confronting evidence and refining ideas. Entropic gravity stands as an example of this process at work. It presents a bold possibility rooted in thermodynamics and information theory, one that inspires new questions and new approaches. Whether it ultimately becomes part of the accepted description of gravity or serves as a conceptual stepping stone toward a deeper understanding, it plays a meaningful role in the ongoing effort to unify the laws of nature. The value of examining entropic gravity lies not only in assessing whether it can replace existing theories, but in understanding how it frames the scientific search for deeper principles. Gravity has always challenged physicists to look beyond the obvious. Newton revealed that the same rule guides a falling apple and the orbit of the moon. Einstein revealed that gravity is not a force, but the manifestation of curved space-time. Verlinde's proposal pushes this evolution further by suggesting that space-time itself, along with its curvature, may emerge from microscopic informational processes. Even if future theories refine or replace his work, the questions he raises remain an essential part of the scientific journey. One of the most important contributions of the entropic perspective is the way it highlights the role of horizons. Horizons are not merely mathematical boundaries. They are physical surfaces that carry temperature, entropy, and informational content. These properties are difficult to reconcile with the idea that space-time is fundamental. They instead point toward a deeper structure in which the microscopic degrees of freedom responsible for entropy become relevant. Entropic gravity interprets these features as evidence that gravitational behavior arises from statistical tendencies encoded on such surfaces. The success of this interpretation depends on identifying the underlying mechanisms, but the thermodynamic behavior of horizons is a powerful clue that information plays a foundational role in gravity. Another contribution of the entropic picture is the connection it draws between entanglement and geometry. The holographic principle shows that the information content of a region of spacetime scales with its boundary area rather than its volume. Quantum entanglement reveals how patterns of correlation can generate geometric connections. These insights suggest that the structure of spacetime may arise from informational constraints. Verlinde's work builds on this idea by proposing that gravitational attraction results from changes in the informational structure when matter moves. Even if his specific implementation does not explain all observations, the underlying insight remains influential. It encourages physicists to explore how entanglement and information might give rise to geometry and gravitational behavior. The debate surrounding entropic gravity also highlights the importance of precision in scientific theories. A theory is not accepted because it is elegant or conceptually appealing. It must match observational data with extraordinary accuracy. Dark matter models, for example, are not accepted because they are aesthetically satisfying. They are accepted because they explain a vast range of observations, from galaxy rotation curves to gravitational lensing to the cosmic microwave background. For entropic gravity to compete, it must provide predictions of similar breadth and precision. At present, it does not, though the concepts it presents may influence future developments that bring us closer to a complete understanding. Another instructive feature of this debate concerns the nature of emergence. Many aspects of the physical world are emergent. Temperature, pressure, and fluid behavior arise from microscopic interactions that cannot be seen at macroscopic scales. The entropic view suggests that gravity might belong to this category. If true, then attempts to quantize gravity directly may be misdirected. Instead of quantizing the emergent behavior, we would need to identify the microscopic degrees of freedom and the rules governing their interactions. This perspective shifts the path of research toward identifying the fundamental informational or quantum mechanical constituents that produce spacetime geometry. Still, emergent gravity models face a formidable challenge. They must not only reproduce the successes of general relativity and dark matter, but also clarify the microscopic framework from which spacetime arises. This framework must be consistent with both quantum mechanics and thermodynamics. It must explain how information is stored and processed, how entanglement generates geometry, and how the familiar laws of physics emerge from these processes. These demands reveal the scale of the task ahead and underscore why entropic gravity remains a conceptual framework rather than a complete theory. One of the strengths of Verlinde's idea is that it aligns with several known features of gravitational systems without requiring new forms of matter or new physical forces. It takes seriously the idea that information and entropy play fundamental roles in gravitational behavior. It connects the thermodynamic properties of horizons with the geometric structure of spacetime. It provides a conceptual foundation that may help guide the development of a quantum theory of gravity. Even critics of emergent gravity often acknowledge that these insights are valuable contributions to modern physics. The examination of entropic gravity reveals a broader truth about scientific inquiry. The search for understanding often leads through conceptual terrain that is uncertain, incomplete, and challenging to map. Ideas like entropic gravity are important not only because they might be correct, but because they force us to examine what we believe and why. They highlight the gaps in our current theories and encourage exploration in new directions. Whether or not gravity is ultimately found to be emergent, the effort to understand its origins deepens our appreciation of the universe and sharpens the tools with which we study it. Entropic gravity, therefore, stands as a reminder that even the most familiar aspects of reality may hide surprising depths. The force that seems so simple, guiding apples to the ground and planets around stars, may be rooted in the behavior of microscopic information. The next steps toward understanding this possibility lie in the search for the microscopic structure of space-time itself, the hidden architecture that gives rise to geometry, thermodynamics, and the flow of time. The deeper we follow the clues hidden within gravity, the more the universe begins to resemble a system built from information, rather than from continuous matter and geometry. Quantum mechanics, which governs the smallest scales of reality, contains structures far more intricate than simple particles and waves. Among its most striking features is entanglement, the invisible thread that ties quantum systems together in ways that defy classical intuition. Entanglement does not diminish with distance. It creates correlations between systems that cannot be explained by any local mechanism. Over the past decades, physicists have discovered that these entanglement patterns may not only influence matter, but may also define the geometry of spacetime itself. If gravity is emergent, then entanglement is one of the most likely candidates for the microscopic structure from which spacetime arises. The connection between entanglement and geometry became clearer through developments in holographic dualities. In certain settings, such as those described by ADS-CFT, the geometry of a higher dimensional gravitational spacetime corresponds exactly to the entanglement structure of a quantum system defined on a lower dimensional boundary. This correspondence is not metaphorical. It is a mathematically precise statement. Remarkably, the shape of the bulk spacetime can be reconstructed from the entanglement entropy of regions on the boundary. This entropy measures how intertwined the states of the system are, and it determines geometric quantities such as areas and distances. In this framework, geometry is literally built from entanglement. The smoother the entanglement across a region, the smoother the geometry becomes. When entanglement weakens, the geometry can pinch, fold, or even disconnect. One of the most important results revealing this relationship is the Ryu-Takayanagi formula, which states that the entanglement entropy of a region in the boundary theory is proportional to the area of a minimal surface in the bulk that corresponds to that region. This result mirrors the area-dependent entropy of black holes and provides a bridge linking quantum information to geometric structure. The formula suggests that the area of surfaces in spacetime is not a primitive feature, but a quantity determined by deeper informational relationships. The geometry emerges because the entanglement structure imposes constraints on how the bulk must be formed. The idea that spacetime geometry might be woven from quantum entanglement gains strength when we examine how different patterns of entanglement create different shapes in the bulk. Highly entangled systems produce smooth and connected geometries. Systems with disrupted or reduced entanglement produce fragmented or distorted geometries. This relationship suggests that the classical behavior of gravity, which depends on the curvature of spacetime, arises from the statistical properties of entanglement. If curvature corresponds to changes in entanglement, then gravity itself emerges as a response to how information is distributed. The motion of objects along geodesic paths reflects the tendency of the underlying entanglement structure to maintain equilibrium. Quantum error correcting codes provide another window into this idea. These codes distribute information redundantly across many degrees of freedom in such a way that the information can be recovered even if some parts are lost. Remarkably, the mathematical structure of certain quantum error correcting codes resembles the structure of holographic spacetimes. The redundancy built into the codes corresponds to the way bulk information can be reconstructed from multiple boundary regions. This insight suggests that spacetime may operate like a quantum code that protects information by encoding it in geometric relationships. The robustness of the geometry, including the stability of gravitational behavior, could arise from the intrinsic error-correcting properties of the underlying quantum system. Tensor network models provide even more concrete demonstrations of how geometry can arise from entanglement. In these models, quantum states are built from networks of interconnected nodes, each representing a mathematical operation. The connectivity of these nodes defines a geometric structure that resembles a discretized spacetime. When entanglement is organized in particular patterns, the resulting network reproduces the curved geometries associated with gravity. This correspondence does not prove that spacetime is literally a tensor network, but it shows that entanglement can create geometric structures that behave in ways similar to classical gravity. These developments point toward a profound shift in how physicists understand spacetime. Instead of being a fundamental background, spacetime may emerge from the entanglement structure of a more basic quantum system. Distances, areas, and curvature could all arise from informational properties. The motion of objects through spacetime would then reflect the behavior of the underlying entanglement patterns. In this view, the force we call gravity is a manifestation of how quantum information rearranges itself. Entanglement offers a powerful lens for understanding how spacetime might emerge, but its implications reach even further when we consider how quantum systems behave collectively. At the microscopic level, quantum states do not simply coexist. They form webs of correlation that determine how information is shared across the system. These webs are not random. They follow precise mathematical rules that dictate which states can coexist and how their probabilities intertwine. When many such correlations overlap, they create patterns that resemble the connective tissue of a geometric space. The remarkable discovery of recent decades is that these patterns can replicate not only the shape of spacetime, but also the dynamics that govern gravity within it. One of the clearest examples of this connection lies in how bulk regions can be reconstructed from subsets of boundary information. In holographic settings, information about a point in the bulk is not stored in a single location on the boundary. Instead, it is encoded redundantly across many regions, allowing the bulk point to be recovered even if parts of the boundary become inaccessible. This redundancy is not incidental. It reflects the underlying entanglement structure. The same property appears in quantum error correcting codes, where information is protected by distributing it across many qubits. The robustness of emergent geometry mirrors the robustness of encoded quantum information. This insight suggests that gravitational stability may arise because spacetime possesses built-in error correcting properties. Curvature, connectivity, and even causal structure could all be side effects of how the universe protects and organizes information. This idea becomes especially striking when we consider what happens when entanglement is disrupted. In quantum systems, the removal of entanglement between regions reduces the ability to reconstruct information across boundaries. In the holographic picture, this reduction corresponds to the shrinking of geometric connections in the bulk. If the entanglement decreases enough, the bulk can disconnect entirely, producing separate geometric regions. This mirrors the way wormholes in theoretical spacetime models can open or close depending on the degree of entanglement between subsystems. The link between geometry and quantum information therefore extends beyond static shapes. It influences dynamic processes and the evolution of spacetime itself. These insights align naturally with the idea that gravity arises from the behavior of the underlying quantum information. If geometry is built from entanglement, then changes in entanglement must influence geometry. The curvature that we interpret as gravity could correspond to variations in the entanglement structure. In this view, mass and energy do not literally bend spacetime. They alter the informational relationships between regions, and this alteration produces the emergent effect we call curvature. Objects follow geodesic paths because those paths represent the most stable or efficient way for information to remain coherent across entangled regions. Gravity becomes not a force, but a reflection of how the microscopic structure prefers to arrange itself. Another deep connection appears in studies of quantum complexity, which measures how difficult it is to construct a particular quantum state from simpler ones. Physicists have discovered that the growth of quantum complexity in certain systems resembles the growth of spatial regions in the bulk. This suggests that the passage of time and the expansion of space might be tied to the evolution of computational processes within the underlying quantum system. The idea is speculative, yet it complements the broader theme that spacetime is not fundamental. Instead, it arises from rules governing quantum information. These relationships do more than describe geometry. They hint at a possible path toward unifying gravity with quantum mechanics. If gravity emerges from entanglement, then the problem of quantizing gravity becomes a question of understanding the quantum system that gives rise to entanglement patterns. Instead of forcing general relativity into the framework of quantum field theory, one can search for the microscopic rules that generate both quantum behavior and spacetime geometry. This approach bypasses many of the difficulties that plague attempts to quantize gravity directly, because it starts from the premise that spacetime is not a fundamental variable. The idea that geometry depends on entanglement also explains why black hole entropy follows an area law. If the degrees of freedom representing a region are encoded on its boundary, then the number of possible entangled states is proportional to the boundary area. This matches the observation that black hole entropy scales with horizon area rather than volume. It also explains why the interior of a black hole appears to store information despite being inaccessible. The information is encoded on the horizon, consistent with the idea that surfaces, not volumes, hold the fundamental degrees of freedom. These insights reveal a universe in which the microscopic structure of spacetime is not geometric, but informational. Entanglement, redundancy, and complexity form the foundation. Geometry arises only when these features organize themselves into coherent patterns. Gravity, in turn, emerges from how these patterns change. This perspective does not diminish the beauty of classical spacetime. It explains it. It shows why geometry is smooth on large scales, and why gravity behaves according to simple rules, even though the underlying structure is far more intricate. If spacetime emerges from entanglement, then gravity becomes a phenomenon woven from the flow and arrangement of quantum information. This perspective naturally leads us to consider how these informational structures evolve and how their collective behavior might generate the classical laws we observe. The remarkable insight is that geometry, causality, and gravitational attraction may all be large-scale reflections of how information is stored, shared, and reorganized within an underlying quantum system. Understanding these ideas requires examining not only the static patterns of entanglement, but also the dynamic ways in which quantum states respond to changes in matter and energy. One of the most striking demonstrations of this dynamic connection arises when we consider how entanglement changes in response to the presence of mass. In holographic models, adding mass to a region of the boundary theory alters the entanglement structure, which in turn reshapes the geometry of the bulk. This reshaping mirrors the way mass curves spacetime in general relativity. The force presence of mass reduces entanglement across certain regions, creating distortions in the informational fabric. These distortions manifest as curvature. Objects moving through this geometry follow paths that reflect the informational constraints. In this view, the gravitational attraction between bodies is not produced by a force, but by the structure of entanglement adjusting to maintain equilibrium. The more massive an object, the more it disturbs the entanglement landscape, and the stronger the emergent curvature becomes. This perspective becomes even more vivid when we consider how horizons emerge in holographic systems. A horizon forms when certain regions of the underlying quantum system become inaccessible to an observer. The boundary between accessible and inaccessible regions carries entropy that reflects the number of ways information can be arranged. This entropy corresponds to the surface area of the horizon in the bulk. The thermal behavior associated with horizons, such as Hawking radiation, arises from the way quantum information straddles the boundary. If entanglement defines geometry, then horizons are natural consequences of the structure of entanglement. They are surfaces where the informational links that support reconstruction weaken or break. The thermodynamic properties of horizons are therefore windows into the microscopic structure of spacetime. The Unruh effect also becomes clearer through this lens. An accelerating observer perceives a warm bath of particles because acceleration changes the way entanglement is partitioned across the observer's horizon. What appears as temperature is the informational consequence of slicing the quantum vacuum in a non-inertial frame. This interpretation illustrates how thermodynamic quantities can emerge from entanglement and supports the view that space-time dynamics, including gravitational behavior, are tied to informational processes. Another important aspect of the informational picture involves understanding how classical space-time emerges from inherently quantum behavior. In ordinary quantum systems, coherence and superposition dominate at small scales, but classical behavior emerges when large numbers of degrees of freedom act collectively. The same principle likely applies to space-time. At the microscopic level, the universe may consist of entangled quantum states with no classical geometry. As these states combine and interact, patterns of entanglement produce a stable emergent geometry that behaves like the smooth space-time described by general relativity. The classical limit arises when the microscopic fluctuations average out, leaving behind a coherent structure whose behavior can be described by Einstein's equations. Recent research even suggests that the Einstein field equations themselves may correspond to entanglement equilibrium conditions. If a region of spacetime deviates from its equilibrium pattern of entanglement, the system responds by adjusting its geometry. The resulting equations resemble those of general relativity. This interpretation points to a possible origin for the dynamical laws of gravity. They may arise as conditions that maintain consistent entanglement patterns within the underlying quantum system. Gravity would then be the macroscopic expression of the system's effort to preserve informational balance. These ideas do not yet form a complete theory, but they provide a compelling path for exploring the microscopic structure of space-time. They unify several key observations. They explain why black hole entropy scales with area, why horizons behave thermodynamically, and why geometry can be reconstructed from entanglement patterns. They suggest that space-time is not fundamental but emergent, formed from deeper informational relationships. And they reveal why classical gravity appears so smooth and geometric, even though the underlying structure is quantum mechanical. This perspective does more than offer conceptual unity. It reshapes the scientific questions we ask. Instead of wondering how to quantize gravity, we ask what quantum system produces spacetime. Instead of treating geometry as a starting point, we treat it as an output. Instead of seeking gravitons, we seek the microscopic variables that encode entanglement patterns. This shift in perspective is not merely philosophical. It guides research toward models that treat gravity as an emergent property and away from models that treat it as fundamental. If entanglement and quantum information determine the shape of spacetime, then gravity becomes a thermodynamic phenomenon emerging from statistical tendencies. The ideas explored in this chapter show that such a perspective is not speculative fantasy, but a reasonable extension of established principles in quantum physics and holography. The universe may not be built from smooth geometry, but from patterns of information whose collective behavior gives rise to the world we experience. The universe reveals its hidden depths, not through what we see, but through what we cannot. Every spiral galaxy that stretches its luminous arms across the cosmic dark is wrapped in an invisible halo whose presence is betrayed only through the motion it commands. The stars at the edges of these galaxies revolve far faster than the visible mass can support. If only the luminous matter were present, these stars would scatter into intergalactic space. But they do not. They remain bound as if held by an unseen hand, suggesting that something vast and invisible shapes their orbits. This phenomenon, confirmed across thousands of galaxies, forms one of the central mysteries of modern astrophysics and defines one of the greatest challenges for any theory that seeks to reinterpret gravity. Emergent gravity enters this domain with bold intent, proposing that the deviations from Newtonian behavior on galactic scales might arise from the informational structure of spacetime rather than from unseen matter. Verlinde suggested that when gravity becomes extremely weak, the hidden elastic properties of the universe's informational background contribute an additional gravitational pull. In his framework, the universe subtly resists the displacement of matter, producing an effect that mimics the influence of dark matter without requiring additional mass. When applied to certain galaxies, this idea captures the broad shape of their rotation curves, offering a tantalizing glimpse at how emergent behavior might complement classical expectations. But the cosmos is not simple. Galaxies vary in size, brightness, density, and structure, and emergent gravity must match this diversity with precision. Observations of low surface brightness galaxies, where the gravitational discrepancy is particularly pronounced, reveal both agreements and disagreements with emergent predictions. Some galaxies appear to obey the additional acceleration predicted by Verlinde's equations, while others diverge significantly. Dark matter, though unseen, explains this diversity by forming halos whose shapes and densities naturally vary. Emergent gravity lacks such flexibility without additional assumptions. Its explanatory power wavers as the complexity of galactic dynamics grows. The challenge deepens when we look beyond galaxies and examine systems where gravity asserts itself on truly enormous scales. Galaxy clusters are immense cosmic structures composed of hundreds or thousands of galaxies bound together by a gravitational force far greater than the sum of their luminous mass. The motions of these galaxies and the temperature of the orbiting gas reveal that a massive unseen component dominates the system. Emergent gravity, in its current form, cannot account for this enormous gravitational influence. The discrepancy is far larger than in individual galaxies, forcing the theory to stretch beyond its intended regime. The Bullet cluster delivers the most dramatic testimony. When two clusters collided at high speed, their hot gas clouds crashed together and slowed dramatically, producing a bright X-ray glow at the center. But gravitational lensing revealed that the majority of the mass continued forward with the galaxies rather than remaining with the slowed gas. This separation between luminous matter and gravitational influence is difficult to explain without dark matter. Emergent gravity does not provide a natural mechanism for such behavior, since its additional acceleration is tied to the distribution of visible matter. The Bullet cluster reveals that whatever produces the missing gravitational mass is not tied to the luminous matter's behavior in simple ways. It behaves like something independent, something collisionless, something consistent with dark matter. The cosmic microwave background adds even greater pressure. Its faint temperature ripples form a snapshot of the universe shortly after its birth, revealing the density variations that would later grow into galaxies. These ripples contain precise information about the amount of dark matter present at that early time. The observed pattern matches the predictions of a universe containing dark matter with extraordinary accuracy. Emergent gravity cannot reproduce this pattern as currently formulated. Without this match, no theory can rival the standard cosmological model. Large-scale structure formation reinforces the same conclusion. Computer simulations of cosmic evolution reveal that dark matter must form the gravitational scaffolding upon which galaxies assemble. The filaments and voids observed in the modern universe mirror these simulations with striking fidelity. Emergent gravity, which lacks a complete cosmological framework, cannot yet produce these structures. Even so, emergent gravity is not without value. It draws attention to the fact that gravitational behavior in extremely low acceleration regimes might involve subtleties not captured by Newtonian gravity alone. It hints that the informational structure of spacetime might contribute small effects that complement, rather than replace, the influence of dark matter. The universe may therefore contain both emergent gravitational behavior and genuine unseen matter, each shaping the cosmos in its own way. This possibility transforms the conversation from competing explanations to layered understanding, revealing that gravity may be richer than either approach alone suggests. If gravity is emergent rather than fundamental, the universe becomes a far stranger and more intricate place than classical intuition suggests. Instead of treating space-time as a smooth continuum, we must imagine it as a vast collective phenomenon arising from countless microscopic degrees of freedom. These degrees of freedom might resemble quantum bits, entanglement structures, or informational nodes far removed from ordinary geometric description. Space-time would not exist at the deepest level. It would appear only when these microscopic variables arrange themselves in the right patterns, just as liquid water appears only when a collection of molecules forms the correct phase. Gravity would then be a large-scale statistical effect, not a basic interaction. This shift is profound. It implies that geodesics, curvature, and even the familiar flow of time emerge from the probabilistic patterns of the underlying quantum system. Mass and energy would not bend space-time in any literal sense. They would perturb the microscopic structure, forcing the system to reorganize itself in ways that maintain informational equilibrium. The resulting rearrangement would appear at macroscopic scales as curvature. Objects following geodesics would simply be following the paths preferred by the underlying informational rules. Perhaps the most surprising implication involves locality. In emergent frameworks, the apparent separation between regions of space may not be fundamental. Two points that appear far apart could correspond to degrees of freedom that are close in the underlying structure. This perspective explains why quantum entanglement can generate instantaneous correlations. These correlations do not violate locality. They precede locality. Locality itself emerges only when the entanglement network organizes into a structure that resembles classical geometry. Horizons take on new meaning as well. If space-time is emergent, then a horizon marks not a physical barrier, but a boundary of accessible information. The thermodynamic properties of horizons arise naturally because they correspond to places where the emergent description breaks down. Singularities, similarly, would not represent physical infinities, but points where the emergent description ceases to apply. Beyond the singularity lies the microscopic domain, where the true degrees of freedom dominate. Even Einstein's equations may be reinterpreted. Several researchers have shown that they can arise from conditions ensuring equilibrium of entanglement entropy. In this view, general relativity is the hydrodynamics of the informational microstructure. Just as the equations of fluid dynamics govern water without referencing individual molecules, Einstein's equations govern emergent spacetime without referencing the underlying degrees of freedom. This framework does not negate dark matter or dark energy. Instead, it reframes them. Dark matter may exist as a physical substance, while emergent gravity describes how the geometry that dark matter interacts with comes into being, or some fraction of gravitational anomalies may arise from emergent effects. The universe may not choose one explanation. It may employ several simultaneously. Emergent gravity therefore changes not only the answers but the questions. Instead of asking how to quantize gravity, we ask what quantum system produces spacetime. Instead of seeking gravitons, we seek fundamental informational elements. Instead of treating geometry as basic, we treat it as a shadow cast by deeper rules. Gravity stands at the boundary between the known and the unknown. On one side lies general relativity, the most successful gravitational theory ever developed, describing the curvature of spacetime with astonishing accuracy. On the other side lie the deep thermodynamic and informational clues, suggesting that this curvature is not fundamental. Black hole entropy scales with area, horizons possess temperature, and entanglement patterns appear to give rise to geometric structure in holographic models. These clues whisper that spacetime might be woven from information, that gravity might emerge from microscopic rules we have not yet uncovered. The evidence forces a dual conclusion. General relativity remains indispensable. Dark matter remains essential. the universe behaves as if enormous quantities of unseen mass shape its evolution. Emergent gravity, as currently formulated, cannot replace these pillars. It cannot reproduce the cosmic microwave background, nor the lensing seen in galaxy clusters, nor the structure of the cosmic web. And yet, the thermodynamic behavior of horizons, the entanglement structure of quantum systems, and the holographic principle all demand explanation. They point to layers of physics beneath geometry, waiting to be revealed. The truth may be a synthesis. The universe may contain dark matter as a genuine substance, while gravity emerges from informational rules. Or emergent effects may subtly modify gravity in certain regimes, while dark matter governs the larger scales. Or both perspectives may be shadows of a deeper theory, unifying quantum mechanics, thermodynamics, and geometry in ways we have not yet imagined. And there, at the meeting point of these clues, lies the mystery. If space-time is emergent, what is it emerging from? What is the nature of the quantum substrate, whose entanglement patterns give rise to space, time, and gravity? What hidden degrees of freedom shape the fabric of reality? Why does the universe encode information on surfaces? And why does entropy guide geometry? These questions hover at the edge of our understanding, like distant stars glimpsed through cosmic fog, their light reaching us, but their nature still concealed. The scientific journey continues into this unknown. We stand in a universe where gravity behaves with the precision of Einstein and the whisper of thermodynamics, where dark matter sculpts galaxies, but information may sculpt space-time itself. And somewhere beneath these layers lies the answer, waiting for the moment when theory and observation converge to reveal the true architecture of the cosmos.